honor to be here. My first trip abroad since the before time. So, all right, this is going to be a more math talk. But fortunately, some of what I want to do has already been covered. So I want to talk about formal number theory very briefly. There's some controversy about whether they start with 1 or 0. I'm going to start with 1. We have the formal axioms, the piano axiom. And a natural question is, all of mathematics just a study of the formal consequences of these axioms? And if that's true, where does that leave the study of infinity? Okay, moving beyond number theory, there's second order number theory. So there the objects are the natural numbers together with all sets of natural numbers. We have the formal axioms of second order number theory. I'll call that PA2, 2 for second order. We have the algebra axioms, the induction axiom, and the comprehension axiom. So we have two fundamental structures of mathematics, the structure of the integers and the structure of second order number theory. The epsilon is just to tell you which integers are in which sets. Okay, so famous theorem of Wiles. Suppose you have a number n bigger than 2, then for all natural numbers x, y, and z, x to the n plus y to the n doesn't equal z to the n. Curious fact, Wiles' proof is not a proof in ZFC, the original proof. And it's certainly far from a proof in even second order number theory. And I'll give you a sociological proof of that. I asked Taylor, Wiles' collaborator, whether it was even a proof in second order number theory, and he said he had no idea. So one can ask the question, can Wiles' theorem be proved from just piano arithmetic? As a question of whether you need infinity in the proof. I claim that's the wrong question. So let's abandon infinity altogether. Let's invent finite number theory. So in finite number theory, the objects are the natural numbers starting with 1 and up to some largest number that's not specified. Okay, so you can write down the algebra axioms. This is not addition and multiplication mod n. So the algebra axioms have to cover the cases where x plus y is not defined because it's too big. But if you sit down, you'll come up with the algebra axioms. The question is, how should you formulate the induction axiom? There are two ways to do it. They're not known to be equivalent. This is the pigeonhole principle. So remember, our universe now is 1 up to n, and we want to capture induction. So instead of saying if I have a formal property that defines a set of numbers and it's not empty, it has a least, it's if I have a formal property that defines a function of numbers, it's 1 to 1 if and only if it's onto. More powerful than the induction axiom, than the usual formulation. Okay, so for each natural number n, if we look at the numbers 1 up to n, that's a model of finite arithmetic. And there's some very simple models. The model whose only integer is 1 is such a model. Okay, so if you work in finite arithmetic, it's an amusing exercise. You can show that z equal x to the y can be defined in finite arithmetic. Remember, it's not total, but you can define it. So that means Fermat's last theorem is a statement of finite arithmetic. You can express it in finite arithmetic. Can you prove Wiles' theorem in finite arithmetic? If the answer is yes, then mathematical infinity plays absolutely no role in Wiles' theorem. You're not going to use asymptotic methods in finite arithmetic. You can't let things get very large and take a limit. It's got to you have to have precise estimates. Okay, now it turns out that many of the main open problems in number theory can be reformulated in finite arithmetic. The Riemann hypothesis can be reformulated in finite arithmetic. And it's interesting, the perspective of finite arithmetic generates many new questions. So is all of mathematics really just a study of the formal consequences of finite arithmetic? Well, let me give you a simple example. You might say, look at Euclid's theorem that there are infinitely many prime numbers. That makes no sense in finite arithmetic. But there's a deeper statement that does, and that's Bertrand's postulate, which is that for every number bigger than or equal to 1, if you look at the interval from n to 2n, there's a prime number. So that clearly gives Euclid's theorem. So if you look at, so this theorem was first proved in the late 1800s by Chebyshev. Erdos found an elementary proof. And if you look at that proof, you could probably prove the lemma in finite arithmetic. If 2 to the n exists, then there's a prime number in the interval from n to 2n. You have enough room. But what if you just know that 2n exists? 2n might be the largest number. You can't do those sums that Erdos used. You would need maybe a different proof, maybe a more careful proof, maybe a more informative proof. I have no idea. I just wanted to illustrate how taking standard statements and recasting them in finite arithmetic, you get new questions. Okay, so I want to remind you about Ramsey's theorem. So I need to set up some notation. If n's a natural number, we'll call a set x an n set if x has exactly n elements. So one set are sets which have only one element, two sets, and so forth. For every set y, I can look at all of the n subsets of y. So those are all the n sets x, such that x is a subset of y. And with that notation, if I was pointing my thing at the right point, we have Ramsey's theorem. So for every natural number n, that's the number of colors. For every k, that's how big a thing I'm looking for. There's a natural number m, so that if you color the n sets from 1 up to m, subsets of that, with n colors, you can find a k set, all of whose n sets are colored the same. Okay, so a lot of quantifiers here. But it's kind of, we're coloring n sets with n colors. We'd like to find a set, all of whose n subsets are colored the same color. And Ramsey's theorem tells us that this is possible. There's the infinite Ramsey theorem. Color all the n sets of integers with n colors, and then you can find an infinite set of integers, all of whose n sets are colored the same. Oops. Ramsey's theorem is proved in arithmetic. In fact, there's a stronger theorem that's proved in finite arithmetic. The infinite Ramsey theorem is proved in second-order arithmetic because we're talking about arbitrary colorings. Okay, now we're going to make a slight change. And this is the Paris-Harrington. It looks just like Ramsey's theorem. There's no size now. It's for every natural number n. We can find an m so large that if we color the n sets here with n colors, we can find a set, all of whose n sets are colored the same. Make it non-trivial. We want the set to have at least n elements in it. Now we're going to do something strange. We're going to require that that set have more elements than its least element. So we're going to couple into the order. So this follows easily from the infinite Ramsey theorem. You just, instead of doing n sets, you do n plus 1 sets. You do a slightly clever coloring. You get an infinite set. all of whose n plus 1 sets are colored the same, so it has more elements than its least element, and then that's how you get the theorem. So you use infinity to prove the Paris-Harrington theorem, even though it's a statement about numbers. And the main theorem is that this theorem cannot be proved in PA unless PA is inconsistent. And in fact, out of that analysis, there's an amusing corollary. This statement in number theory is equivalent to Goodstein's theorem. And the only known proof of that is to drill down into proof theory and look at the two things. So this is another manifestation of Goodstein's theorem. Okay, but we can use the Paris-Harrington theorem to define some very large numbers. So for every natural number n, we'll let PHN, that's for Paris-Harrington, n, be the least m that witnesses the Paris-Harrington theorem for n. Paris-Harrington theorem tells us that you give me the n, there's this m with this nice property, we look at the least one, that's the Paris-Harrington number for n. This is a non-standard nomenclature. These numbers are enormous. PH10 can't be written in decimal notation in our universe. In fact, neither can PH5. PH11 is vastly larger than PH10. So these numbers are getting really big really fast. So now we can do a version of Gödel's second incompleteness theorem. So Gödel's sentences in finite arithmetic. One doesn't normally think of Gödel's sentences as making sense in finite arithmetic. Finite arithmetic proves its own consistency. So it's not like arithmetic. Okay, so you could first devise a formula of finite arithmetic. I want to say I'm PHK. So I say there exists a y is PHK, and 2 to the 2 to the y exists. That gives me enough room to authenticate that what I think is PHX is really x, PHX. That's the point of the double exponential. So now the Gödel sentence. So it's a formal sentence in the language of finite arithmetic, small length, you could write it down. And what this formula or sentence expresses is that there is a proof of its negation. That's a familiar component in the Gödel incompleteness theorem. But from finite arithmetic of length less than PH10, that's a knob you can turn, and PH100 exists. Okay? And we express that by saying that this formula holds of 100. So the sentence says there's a proof of my negation of some length, but some much larger number exists. That's the wrinkle. Okay? Well, assume PA. Well, then there is a proof of the negation of this sentence from FPFA of length PH11. But how do we know there's no proof from FPA of length less than PH10? Would we care? Well, wait a minute. If there's a proof of this sentence from FPFA of length less than PH10, the sentence is true unless PH100 doesn't exist. So if there was a proof of length less than PH10, large finite would be contradictory. You couldn't have PH101, for example. So that would be bad news for mathematics. That would wipe out all of mathematics. It's not saying that infinity is inconsistent. It's saying that large finite is inconsistent. Okay. That would be a bad day, especially for me. All right. So how can we secure the finite against this? Well, as I said, from arithmetic, we can prove there's no proof. Remember, this is our question. Is there a proof of this sentence from FPFA of length less than this very large number? Well, PA proves that. But why does that mean there's no proof? Okay, well, can we do better? Oops, sorry. Okay. You're right, this is very complicated. Okay. Okay. Well, in FPFA, if you assume pH 101 exists, then there's no proof of length less than pH 10. This isn't helping. Why do we know that pH 101 can exist? These are very big numbers. So the real question is, how do we know we cannot find by any physical or mathematical means a proof of the negation of this Gödel sentence from FPFA of length less than 10 to the 24th? Maybe I flip 10 to the 24th quantum coins, I get an output, I plug it into my proof verifier, and lo and behold, it's a proof of FPFA of that not theta G holds. I would then have my evidence that large finite is inconsistent. Doesn't affect anything I see about the world, because you can't use pH 50's existence to rule out this string. And pH 50 is far more complicated than anything that we see in the world. So how can we be sure we can't find accessible, verifiable evidence which converts to a proof of the negation of this sentence from finite arithmetic of length less than pH 10? You might say, well, it's obvious that pH 100 or 101 can exist. Why? The only argument I can see that pH 100 exists is that pH n exists for all n. How are you going to distinguish pH 100's existence? Remember, that's a huge number. Why should it exist? Arithmetic can't prove it exists for all n. It can prove pH 100 exists, but that's a very long proof. Inaccessible in this universe. Okay, so if we want to secure the finite, let's secure the infinite. Obviously, if the infinite doesn't lead to a contradiction, the finite can't lead to a contradiction. And it should be easier to find the contradiction in the infinite. So the simplest setting for the study of the infinite is second-order number theory. And we have the axioms, PA2. So can we answer the basic questions of second-order number theory using or starting from these formal axioms, and thereby show our conception of arbitrary sets of natural numbers makes sense? The point is, from the point of view of arithmetic, the only way to argue that pH n exists for all n is to have the totality of the integers. But once you go down that road, you should be able to talk about all sets of integers. So that's the segue. Okay, so I didn't look. I started at...
You're good still. You're doing good.
But I'll be doing good until I'm not doing good. And I'd like to kind of...
You're 20 minutes in.
Okay.
You're 20 minutes
So I have 10 minutes.
Yeah.
Okay, I'm going to speed up. So the standard structure for second-order number theory is really the structure of the real numbers together with simply defined sets of real numbers. These are called the projective sets, and they're not the projective sets in the sense of algebraic geometry. I keep pointing this in the wrong direction. Okay. No, this time doesn't count against me.
Yeah, jag kan inte ens här. Trouble with this.
Maybe the
Pass
better.
on.
Okay.
Lazy.
I think there might be several steps.
Pardon? And it might be what? What am I doing wrong?
I don't know. Now it's working again.
Okay. It doesn't like me. That's clear.
No, it doesn't like you. It doesn't like you.
It doesn't like me.
No.
Okay. There are two mathematically equivalent ways to define the projective sets. There are the sets of reals which are definable in the structure of second-order number theory, logically definable from parameters. That's the logical notion. If you don't like logic, you can define it using calculus. You can look at all the sets of reals which you can generate from the open sets in finitely many steps using the trivial operations of taking a complement of a set, and the other operation is taking the image of a set under a total continuous function. So the total continuous functions are relatively simple at some level. So these are the two simple operations. Close the open sets under these operations. These are the same sets. So we need some questions. Well, we can take standard questions from set theory and localize them to the projective sets. So we can talk about the projective axiom of choice. But to do that, I need to define the projective subsets of the plane. You do it in exactly the same way. Once we have the notion of simple subsets or projective subsets of the plane, we have the notion of function and everything else. So the projective axiom of choice says that if you have a subset of the plane and it's projective, let me draw a picture because that's actually, we'll just do it. Here are my axes. Here's my set. That's my set X. And I want a projective set that does this. So in every vertical line where X has a member, I pick one point, the axiom of choice. But through the lens of the projective sets. And this is the formal thing. I made the set have points above every point, and then my Y has to pick one. That's the formulation of the axiom of choice localized to the projective sets. Well, we can also do the continuum hypothesis. So we look at two projective sets, X and Y. We have the notion of a projective function, a subset of the plane. It's a function whose graph is a projective subset of the plane. And so now we can just projectify the continuum hypothesis. Suppose we have an infinite projective set, then one of the following holds. Either there's a projective bijection of the natural numbers to X is countable, or there's a projective bijection from the reals to X. X has the same cardinality as the set of real numbers, but projectively verified. Whoops, sorry. So we have two questions. The projective axiom of choice, true or false. Projective continuum hypothesis, true or false. Both questions of second-order number theory. These were studied intensively in the early 1900s, and they were considered hopeless problems by 1925, 100 years ago. They're both unsolvable.
Unsolvable, did you say?
Pardon?
I couldn't just hear the last word.
Both of these problems are unsolvable.
Unsolvable.
Yeah, unsolvable. These problems are unsolvable based on the axioms of second-order number theory, but in fact they're unsolvable based on the axioms of set theory itself. And it's essentially the same proofs of Gödel and Cohen. So we have basic questions of second-order number theory, can't solve them even in set theory. I'm starting to feel like,
Yeah, here we
oh,
Here we go.
it's almost like there's a delay. It wants me to click many, many times, and then
Let me move that.
I think
to
it says I'm out of
another
time.
Connection. That might just be the some kind of error on that. So it takes a better signal from there.
Okay.
Here we go.
Hopefully it works better now.
Okay, thank you. Some problems are solvable.
Sometimes.
So maybe not all is lost. Maybe if we sharpen our conception of second order number theory, we can find answers to these questions. Just because they're not answerable based on our initial axioms does not mean that the questions don't have an answer. Okay, so one way to do it, and I'm doing revisionist history now, I'll introduce the concept of a projective frame. That's an extension of the second order piano axioms that's supposed to provide a complete description. That's a vague notion. The extension should be specified by a computable list of formal axioms. And it should be immune to Cohen's method, which is the basic method in set theory that shows problems are unsolvable. And this can be made precise. So there is a projective frame given by Gödel's axiom for set theory, the axiom V is equal to L. That's the Gödel frame. And the Gödel frame implies the projective continuum hypothesis, and it implies a projective axiom of choice. Great. If things were only this simple. There are other projective frames. The Michalski axiom of the axiom of determinacy gives another projective frame. This is the PD frame. The PD frame also implies the projective continuum hypothesis, and it also implies the projective axiom of choice. Well, we could strengthen the continuum hypothesis and formulate the strong projective continuum hypothesis. If X is an infinite projective set and X is not countable, then X contains an uncountable closed set. It's a strong version of the projective continuum hypothesis. It implies the projective equivalence continuum hypothesis. They're not equivalent statements. And then we can strengthen the axiom of choice and introduce the projective well-ordering principle, which is that there's a projective well-ordering of the reals. That's an ordering of the reals such that every subset has a least element. So the projective well-ordering principle implies the projective axiom of choice. The projective well-ordering principle refutes the strong projective continuum hypothesis. And so now we have divergent projective frames. Assume the Gödel frame, then there is the projective well-ordering principle holds. Gödel proved that. Davis's proof of the projective continuum hypothesis within the PD frame actually shows the strong projective continuum hypothesis. And in particular, that the projective well-ordering principle does not hold. So we have incompatible divergent frames. In fact, there's a whole array of projective frames. But many other projective frames were discovered. Cohen's method yields projective frames in which both the projective axiom of choice and the projective continuum hypothesis fail. But for 25 years, the PD frame was really the only frame known in which you had both the projective axiom of choice and the strong projective continuum hypothesis. And a conjecture emerged that the PD frame is implied by those two consequences. Remember, we're trying to figure out truth here. So if this were true, this recovery result might build a case for the PD frame and distinguish it from the other frames. But that turned out not to be true. Assume the PD frame is consistent. There are many projective frames in which the strong projective continuum hypothesis holds, the PD frame does not, and the projective axiom of choice holds. So that hope, yeah,
But these will differ in some, but they differ in some other important way? They diverge in, they're distinct?
yes,
Okay. In what
yes,
sense?
because a PD frame is false.
Oh, but I meant the ones, this whole, of the class of all these projective frames for which all these hold.
There are many of them, yeah.
Right, but do they, in what sense do they differ? Do they differ with respect to?
They differ in the details.
Oh, okay.
Because the projective sets are layered. There's a degree of complexity of the projective set, so you can tunnel in and ask for the nth level sets what's happening, and you can make things go different at different levels.
All right,
I was hiding that.
okay. Sorry.
My point is that it looks like the attempt through the lens of second-order number theory to understand second-order number theory is completely failing. We see all these possibilities, and we have no way of picking one out. Looks like there's no truth. Okay?
Keep going.
Okay.
I think
I'm almost done. So let's change perspective. You know, if you're losing a game, change the rules of the game. So the V perspective, V is for the universe of sets. So the axiom that there is a measurable cardinal is a fundamental large cardinal axiom. A large cardinal axiom is an axiom of set theory that asserts the existence of a really big set. The large cardinal axioms for finite arithmetic are things like the Paris-Harrington numbers exist. Okay, Robotin proved in 1964 that if there's a measurable cardinal, the Gödel frame is false. So the conception of V, the universe of sets, entails rejecting the Gödel frame. So we're making some progress. At least we can throw away one frame. What about the other projective frames? Well, there's an unexpected and perfect alignment. Martin-Steele theorem of 1985, suppose there are infinitely many Woodin cardinals, then the PD frame holds. The PD frame is a one true frame. And in fact, there's a theorem, the PD frame is equivalent to the theory of second-order number theory given by the ZFC axioms together with the scheme of axioms. There are n many Woodin cardinals for each n. An exact match. So we no longer have a multiplicity of frames. We have one, the PD frame. So we now have a new truth of finite arithmetic. The PD frame is consistent. And now I'll make my usual claim. This claim will not have been falsified by the 1000th anniversary of this meeting. So this is supposed to be about consciousness and all of that. Would a Turing machine make this claim? If it was investigating, you handed it the axioms of set theory and say, tell me about the projective sets, it might discover this theorem, but would it move to this claim? Maybe PD is inconsistent. Maybe this hypothesis is inconsistent. How would a Turing machine make that claim? Is it hardwired? How do we make that claim? Is it in our biology? Maybe. Doesn't seem quite right, though. All right, but we have to be fair. I'll end in 3 minutes. But have we succeeded in securing the infinite? We moved to the projective sets to try to secure the finite. Through the lens of second-order number theory, we were making no progress. We then made progress, but by changing the rules of the game and moving to set theory. So we had to enlarge our scope to V. But then fairness requires we should move from considering projective frames to V frames. Otherwise, we're kicking the can down the road, so to speak. So is there an expansion of the ZFC axioms which yields a conception of the universe of sets which is immune to Cohen's method? That was one of our criteria. But now compatible with all large cardinal axioms. This is the large cardinal test. And up to about 15 years ago, this seemed completely hopeless. But there were some misconceptions. So there's the ultimate frame. By generalizing the projective sets to a vastly larger collection of sets of reals, one has led to a generalization of the PD frame in the context of second-order number theory to a single axiom, V is ultimate L, for the universe of sets. This axiom settles the problem of the continuum hypothesis, implies that it's true, and it does much more, it implies PD. The axiom yields a V frame, which is immune to Cohen's method. And that's a precise statement, and it tells you something about the richness of this axiom. But is V equal ultimate L the one true axiom? Does it even pass the large cardinal test? Well, let's go back to Gödel's axiom, V is equal to L. So Scott's theorem, which predated Rowbottom's theorem, assume V is equal to L, there are no measurable cardinals. Now that doesn't tell you that the Gödel frame is false, because that's talking about the reals. Gödel's axiom V is equal to L fails the large cardinal test. We have to reject it. So the ultimate L conjecture is a precise mathematical conjecture, which if true implies that the axiom V is ultimate L passes the large cardinal test. So that's a new ingredient in the story now. The ultimate L conjecture also, if true, provides compelling evidence that the axiom V is ultimate L is the true missing axiom for set theory. Now that's a controversial claim. There may be only one person who actually believes that claim. The ultimate L conjecture is an existential statement of number theory. It must be true or false. It cannot be meaningless. See, the danger is you formulate a conjecture that, like the ultimate L conjecture, to show that this axiom passes a large cardinal test, but this conjecture itself is like the continuum hypothesis. Maybe true, maybe false. The ultimate L conjecture is a number theoretic statement. In fact, it's an existential number theoretic statement. It's got to be true or false under any reasonable conception of truth in number theory. So that's where we are. And there's a methodology for trying to prove the conjecture, and that's underway. It's not like there's no idea what to do. It's just a matter of trying to do it. So set theory at this moment is really at a crossroads. If the ultimate L conjecture is true, it goes one direction. And this whole phenomenon of the ubiquity of unsolvable problems that's sourced by Cohen's method disappears. Because the axiom's immune to Cohen's method. If it goes the other way and the conjecture is false, then the whole methodology developed over the last 50 years for trying to understand the internal structure of the universe of sets fails. So I'm not exaggerating when I say it's a crossroads. And this will get resolved soon. Okay, so I went over a little.
Any projections on resolution?
Well, I'm in the ultimate L conjecture's true camp. Some people like eternal mystery, and so they favor the other route, because then instead of seeing the universe of sets, it just recedes over the horizon into... but I have to say, it's going to be interesting. But it's the first time sets theory has been, it's the first time there's been a candidate for a V frame. It wasn't clear, it's kind of like you're looking for a unicorn. It would be nice to see some approximate unicorns. And the unicorn is the V frame. There were no approximate unicorns. There was nothing. There was no contrived V frame. So we now have a candidate for a V-frame, but we have more than that. We have a way of showing possibly that it passes the large cardinal test. That's the key. V is equal to L is immune to Cohen's method, fails the large cardinal test. It's almost a V-frame, but it fails a large cardinal test. So can you have both being immune to Cohen's method and being a V-frame, therefore, and pass a large cardinal test? There's no example of such an axiom. This is the first candidate. So thank you.
Thanks, Hugh. I'll start with a comment, and hopefully that'll then lead you guys into it all. But I think actually this is very relevant to thinking about how things like the human mind or synthetic minds, like people like Demis are trying to build, need to be thought about. Because I think that the question that you posed sort of about Turing machines and would they have thought about this sort of references some of the very key points about some kind of notions of correlative intelligence versus generative intelligence. Generating these sorts of insights from experience. How do we do it? What are we accessing when we do it? I think it plays a very central role in these things. So I think these are sort of like, we sort of often end up talking about Gödel's theorem as if it's this sort of fairy dust that speaks of some larger universe that we can't or haven't understood. But there's lots of examples. There's lots of examples and lots of important things that we don't understand that seem to signal that there's more than meets the eye, so to speak. So I think this is super relevant, something that for anyone who talks about the mind to try to understand and be able to talk about. Joseph?
I think
Demis, you go.
Yeah, I mean, I think there's a few things to say about this. It's an interesting, it's a challenging question. I mean, the first thing would be to ask if the Turing machine can't do that, well, what is it different about the human mind that is it? I mean, you asked the question, you didn't answer it. Well, how are we coming up with that kind of statement? So you'd have to answer that. I mean, my view is the Turing machine would be able to do that. Unless you think the human mind, there's something magical.
No, so you believe the Turing machine would make the declaration that PD is consistent?
Well, it could do. I don't see why you're sort of saying why would it
the Turing
not be?
machine can make any declaration, program it in. My question is...
The example I'd give, I caution anybody to say these kinds of statements because when I've seen things in equivalent areas like in Go, for example, when Go players who have their own esoteric system, it was imagined for a long while that Go could not be solved by a computer. It was, resistant to that computer. Computer chess was done in 95, Go was done in 25 years, but it turns out it could be done, and actually original ideas could be come up with. Now the interesting question is, could a machine invent Go, not just come up with a brilliant move? And that's a separate question, which is worth discussing.
I think that's still what Hugh is really saying.
Yeah, so
he's invented a game, if you like.
Right.
And this is precisely the key.
I'm coming to that. So for now, AIs can't do that, right? They can come up with a brilliant move, a novel move even, novel strategy, but they can't come up with the game. But I don't see why they wouldn't be able to.
I'll make another prediction. Let's assume in the next 100 years, 1,000 years, we encounter an extraterrestrial civilization that we can communicate with. So they're technologically advanced, just as we are. My prediction is they will have made this prediction. That PD, they will have discovered PD, and they will have declared it's consistent.
So why would you think an AI can't do that? I don't understand. What's the missing thing?
Would you make that prediction about Go, that they've discovered the game of Go?
Potentially, yeah.
You would?
Yeah, for sure. Go is a super simple...
How about chess? Would they have discovered
No, chess maybe not. I think Go potentially...
Okay, so you're drawing, do you think chess, Go is some kind of fundamental invariant? All civilizations discover Go.
I think it's quite fundamental.
Okay, I'm ignorant of Go. I know that I've seen the board, but...
but it doesn't matter about the Go. The point is, why would you say the extra... So if another alien civilization would have come up with this PD conjecture, Why would you not think an AI could do that? I'm just interested to know what's
No,
the difference.
I don't have a position on AI doing it. I'm merely asked.
But you just said Turing machine couldn't do it.
No, I said, could a Turing machine do it?
Yeah, and the answer has to be yes, unless you're saying there's some other reason.
So,
What's
I
the-
No, I think the other alternative reason, of course, is in the way is that, you know, reality is structured differently from current conception, and structures like the human mind do something that extends beyond what
Right,
Turing
so you-
machines do.
I understand. So you-
and in a way, then, like you said yourself correctly, that then, you know, maybe I'll put myself in the we, but not Hugh, have to explain what is it that is
Yeah.
different that we do.
But that's
And-
what I'm interested in. Yes,
Yeah.
exactly. That is isomorphic to that point.
And that is why we are here.
That's
Joseph, let's hear you. We have lots of time. This is
So my question is, you said in passing, kind of in a dismissive way, is it our biology? And I'd like to suggest that it might be our biology that leads us to, among the two schemes you talked about, to the ultimate L. But let's take something simpler that's not. So we were at one point just with finite ordinals, finite natural numbers. That is what we had. We didn't have any extension. We didn't have the notion of infinite ordinals. And one might wonder, is it something in our biology that led Cantor to go for infinite ordinal, for this kind of extension? Because there's other possible extensions to deny that this is possible. All kinds of models can be given to simplify. And maybe it is part of our biology, and maybe of even other species of higher mammals, because we live in reality and not in models, to go for that kind of extension that is truth-seeking, that is attuned to what N is, what R is, what V is, rather than what is possible, so to speak, with some axioms. I mean, I'm simplifying. So it doesn't seem to me clear that biology is not capable of answering. This is independent of artificial intelligence. I mean, there's a further question here. But why is our biology not the answer? Why is it so obvious?
Well, I didn't mean to say it wasn't. I just meant to say, look, if this is a meeting about mind, if mind if the reductionist to current physics for mind is not true, you would like to see actions of mind that couldn't be explained by that reduction. All I'm saying is, here's a possible example. Maybe it is explained by that reduction, but that would be a remarkable fact. You know, I don't know. I'm just saying.
But can I just add a thing about how I understand the word biological?
yeah.
I don't know what reduction, the various kinds of reduction, but our being biological beings does not require materialist or whatever it is, reduction. In the very growth of the species and of species out of species and so on, there is attunement to the structure of reality. Otherwise, you know, the unicorns, you know, kind of go out. I mean, the T-Rex is out and so on. So I'm not sure that, you know, biological has to be understood in a very limited way.
I mean, I'm a biological being, I think. And, so I'm not arguing. I'm just saying the usual idea that set theory is grounded in our physical experience seems a little tenuous to me because it's not obviously present in the world. And the fact that our investigations have been successful where there was no reason to believe that they would be accepted. Why should there be a preferred projective frame? No reason to believe that. In fact, there's every reason to not believe it. So it's like you can paint a box and say, I'm looking for an answer in this box. And then not only do you find the answer, you find just one. It's a remarkable coincidence. That's all I'm saying. You know, it can be a one-off success, but what's happened in the last 15 years 25 years ago, if I were giving my not CH talk, I would be claiming something completely different, and part of that story would have been there is no V-frame. That was very much part of the intuition 25 years ago, and it was based in speculations, technical facts that turned out to be false. There was a very appealing multiverse conception for set theory.
Can I just say, I know that I'm overreaching here, but that this attunement to an overall unique frame might be part of what is written into biological theory. That what you were 25 years ago is a mere modelist, so to speak, rather than a single universe being.
So that might explain why, if there was a V-frame, our biology might lead us to that V-frame. But it gives no reason for why there should be a V-frame.
But hey, guys, can I pause this convo because we've got time offline, and Hugh, I know that Roger has a question, and then I see that Ron's got one too, but then I'm gonna pause that one to post-game so that we can move on to Sabrina's talk. But Roger, would that be okay if...
Yeah. Yes. Well, I'm not sure whether it's one or two questions. When you talk, well, for example, if I get the terminology correct, you talk about pH 15 or something, and whether it exists or not. Now, the term exists, is this talking about how we reason, really? I mean, how we think about... I mean, exists in the sense of physics is very different, or the physical world.
I absolutely agree.
Very different things.
So when I say exists, means it's not contradictory.
Ah, yes.
Okay? So that I can't falsify it.
Yes. So it's basically a. Well, if I use the word logic, it probably restricts the conversation somewhat. But yes,
It's not logically falsifiable.
Yes. No, I take your. Yeah. No, I've got that. Could I ask you a question about just something I've wondered about sometimes? We talk about the continuum hypothesis. Mm-hmm. Now, I just a suggestion, and it probably doesn't. I mean, suppose you think of infinite decimal sets, one way of thinking about it, for which there is a rule about how to generate the numbers, the digits. Now, a rule is a rather vague statement. But somehow you can imagine it could involve diagonalizations and all sorts of things. So it's very vague about it. But a precise rule, so every digit is determined by a rule, and the number of those things, could that be something which is beyond...
Okay, there would have to be lots of rules.
Yes.
So if you assume V is ultimate L, it gives us extraordinary structure to the universe of sets. And under that axiom, every real number is definable from an ordinal.
So, from an ordinal?
Yeah. From an
I see,
ordinal.
yes, well that would be the sort of thing.
That kind of thing. So every real number is definable from an ordinal.
I see.
And then you can calculate the length and you get omega 1, and that's how you get CH. So it's the best approximation you could have to every real decimal expansion being given by a rule. Every rule is definable from an ordinal. In fact, under this axiom, every set is definable from an ordinal. So that explains the axiom of choice, because you can well order a set by ordering the definitions.
Yeah.
So you get V is ultimate L does not. It can be an axiom in ZF. It's not an axiom in ZFC, but it implies the axiom of choice. But it tells you why the axiom of choice is true. I think.
Of course, the general question is, how does this relate to the physical world? I mean, it's the sort of thing I was trying to address.
Yeah.
And of course, these things are in the physical world in the sense that they're part of our way of thinking. So it's through consciousness, if you like, because it's how people like you think about the world, and therefore it gives these things an existence in that sense. But it's quite far removed from the way we think about physics.
It is.
Yes. So it's an interesting question. Will it forever be far removed from physics?
Well, this is a good question. Because a lot of things which are part of physics now,
Infinite dimensional Hilbert spaces.
we're even going back to Newton and Leibniz, the idea of calculus, which,
Yeah, I agree.
yes.
I mean, it would be great if set theory became part of physics. But I'm almost more intrigued by the idea that it's never going to be part of physics.
Yeah.
Because it says there's truth outside of physics.
Yeah.
Which is still part of the way we think, and in that case.
Yeah, but now I may be very simplistic here, but imagine you had a teletype that connected to another universe, and you're trying to find common ground. Set theory is going to be a common ground.
Oh, yeah.
Whereas electrons, protons, GR, not clear that's part of a common ground. Who knows what the physical laws in that other universe are? But set theory is not going to be different.
No, absolutely.
So we'll call that the Turing test for set theory.
And folks, here I say thank you to Hugh and all the questions. I know there's a million more, but we need to get Sabrina Maniscalco on the stage, so thank you, Hugh. I don't know if I love or hate trying to mediate this thing, because at moments I feel like an all-powerful dictator, and then sometimes like an evil leader, crushing people's excellent ideas by accident. So apologies to those who were
I
crushed.
have a question.
Yes.
How much do we have to pay to have the
Oh, no, that can be done. That can be done. I thought that was really good.
I'm just worried I said things.
No, I think it's brilliant. I honestly, I think they should. Let's discuss whether you should.
Let's check that. No, that was great.
My children still remember it.
I mean, I like these things. I think it's great stuff.
I think when you visited Max,
Oh, yes, no, he's
he was. I had to get a car seat. I had to get a car seat. I remember that.
Yes, no, that was absolutely right. Yeah. No, he's just, in fact, he just got a first-class degree in mathematics.
Oh, congratulations.
Should I try talking? How is the...
No, we must talk.
Yeah, I mean, I can tell you that it won't be easy, but yeah, I can try. I can try. Okay, so I guess we wait a bit. I mean, while we wait, I can show you the title of my talk. That is this one. And there is a little bit of something in your order. And I also can tell already now that this will be quite a shift from math to something which is very closely physics related. So it's a math to physics jump. And I think I cannot say anything more before the others are back.
Will the rest come back?
Sorry?
Will the rest come back?
Yeah. I can also tell that.
Even with my glasses on, I can't even read. It's terrible. I should have.
Oh no, maybe you.
Bring your monocle.
I left it behind.
Well,
It's absolutely stupid.
you're in London. I'm really not.
Yeah, no, the monocle is in Oxford.
Oh no.
Yeah.
It's a little thing I can read.
Yes.
Now you have to get about this close in order to read.
The title is the subtle interplay between coherence and noise
Oh, I see. Okay.
in quantum biological systems. And I would say something that goes a little bit more toward the brain also. Of course, I don't have a model in the case of the brain, and I didn't study or I didn't try to model microtubules. But let's see what we can say about it. It's the perspective of a person who has been doing open quantum systems. So I'm an open quantum system theory person. So I study different types of noise on quantum systems.
Okay, well, I'd be very interested to see. Yeah.
Right. We're having a little break, but soon.
today is catching up on the I never stopped talking on the plane, I stopped talking. This is very different from Zoom.
Yeah, of course.
And it's a vital factor which is missing in Zoom here.
Now this is finally beyond. I promise you something new, Dennis. It's coming. Alright, do we have everybody? Okay, I think we almost have everybody. Alright. I feel like I'm as close to having everyone as I'm going to be. So, without further interruption, I give you Sabrina Maniscalco.
Thank you very much. It's great to be here. Thanks a lot. I'm going to talk about the subtle interplay between quantum effects, in particular coherence, noise, and we will see also geometry or topology in biological systems. I will not talk about really the brain, but I will end with some sort of open questions. Some ideas could be applied also to theories of consciousness in the brain. And this is the outline of the talk. I want to start by describing what I think are some misunderstandings about the so-called quantum to classical transition, and I will define it very soon. And then I will describe the framework. The framework is the following. We have whatever system, a certain input or a trigger, a certain evolution or propagation or something happening on the system, and then we had outputs, reactions, measurements. Finally, I will give an example of a very recent paper in which the propagation of quantum energy, so a photon in this case, in fractal networks has been observed in experiments, and I will try to link the two. And finally, I will conclude with open questions. So at the end, I will ask you something. And I think that these are some of the things that are aimed at stimulating discussion. But let's begin with the quantum to classical transition. This is a drawing by Zurek, one of the main scientists in the theory of environment-induced decoherence. And you will see here, what you see here is some sort of line, it's a fuzzy line, between the quantum domains, where we can have Schrödinger-Cat states, where we can have photons, electrons, atoms, all the quantities that are subjected or are ruled by quantum mechanics, and this is the classical realm of sun, planets, us, everywhere that is the world around us, as a matter of fact. And we do not probably really know where biological entities, or even the brain or microtubule, where are they? Where do they sit? What is this border? This is what we are going to discuss. And about the myths and misunderstanding I want to discuss with you, I would like to begin by sort of trying to discuss what do we mean with quantum in quantum biology. The second point I would like to make is that very often we believe that quantum information, this is actually really tricky, quantum information is continuously lost in the environment, and as a consequence, quantum systems become classical. This is really so. The third point is, it is assumed that the larger, the more macroscopic objects are, the faster is the loss of quantumness. Is it always so? And finally, it is also assumed very often that the hotter is the environment, the faster is the loss of quantumness, the faster is the decoherence. Again, how general are these statements? And I would like to begin with point one. When we talk about quantumness, very often we talk about coherence, superpositions, or interference. But this is just one aspect of quantumness in general quantum systems. There exists also entanglement, that are specific quantum correlations, and these are crucial, for example, in quantum technologies. But there exists also correlations which are quantum, but they are more general than entanglement. They are different than entanglement. And finally, we can think in terms of quantum information. So when we describe quantumness, say, in biological systems, we have to specify what we are talking about. Very often we are talking about this, but this is not necessary. We know from quantum information theory that other types of quantum properties may play a key role. Now, this is my attempt to imitate the beautiful drawing of Sir Roger Penrose. I hope I will, in the future, improve. This is my own drawing to highlight one of the main points that I want to make. The point is, the behavior of these quantities in presence of the environment is strongly model-dependent. And because of this, we have to be very careful in drawing general conclusions when we think in terms, or we talk about, the role of quantumness in biological and even bigger systems, and in fact in any quantum systems. Here I give you some examples. I will try to explain briefly, but without describing the theory, of some results that we have been obtained. All of these results that we have been obtaining in theory have been experimentally verified, so they are all confirmed by experiments in which strange things perhaps may happen. Quantum bits interacting with an environment, you can see here that while entanglement decay in time, until it disappears at a certain time, quantum correlations can be completely constant. These quantum correlations are measured by this cord. So they are different properties, very different behavior in presence of an environment. Okay? Another example, this is known as a sudden transition between classical and quantum decoherence. Why classical? Because if we look at classical correlations and at quantum correlations, as indicated by this cord, again, these are qubits in presence of an environment. The environment is there. You lose quantum properties. However, initially, quantum properties are frozen. Only classical correlations decay, and then a transition occurs. So quantum correlation starts decaying, and classical correlations are frozen. Again, it depends on the indicator you're looking at. Even more weird, for certain so-called non-Markovian environments where the spectrum is very structured, you can have quantum properties which are time invariant. Note that the system evolves, just the quantum correlations are not evolving at all. And finally, this is probably very difficult to see. I'm really sorry, the lines are very small. In other papers, we have demonstrated that in certain types of structured environments, quantum correlations as measured by entanglement can be trapped. Entanglement trapping exists. There can be physical systems subjected by very weird type of noise where entanglement is actually completely non-decaying, but trap remains. Okay? Now this is to say that in general, a lot of phenomenology can be observed. So second point I want to make, quantum information is continuously lost in the environment. Here I won't start defining what are the different indicators of quantum information, but if you are interested, I can talk about it. And this is again another theoretical paper, is also this experimental demonstrated, in which you have again qubits interacting with an environment, and you have a certain parameter here that allows to modify the environment at will. What am I plotting here? The red line is the presence of stationary coherences. So this means I have a qubit, the qubit is in a quantum superposition, I wait for a very long time, coherence is still there, it's trapped. So this is a stationary coherence which remains for different values of the different types of environment. And this is associated with the presence of information backflow. Information is transferred into the environment, but part of it comes back and gives rise to this phenomenon. Okay? So again, it is not said that information is just lost. Quantum information is just lost into the environment. It can come back. Now, another very, very common thought is, and again, this was one of the initial criticism when the idea of having quantumness in microtubulus was proposed, is that, well, these objects are actually quite big. You know, I mean, the decoherence time would be so fast that you wouldn't observe any quantumness. And here I will show two examples. The first one is a Schrödinger cut state. So it's a superposition of two macroscopically distinguishable objects in a quantum harmonic oscillator. So you can imagine it as really a superposition of being here or here. It's sort of localized states of the system. And it's a paradigmatic, of course, system in quantum physics. And here you will see a table showing different definition of quantumness. There is not just one. Even for the quantum harmonic oscillator, there are different ways of defining quantumness. Negativity of the Wigner function. I will not describe them all in detail, just to say we don't have a unique way of defining what quantum is. And here you see that depending on the indicator of non-classicality, you have different times at which the system passes from a quantum superposition.
Can I interrupt?
Yes.
One question.
Yes.
What is P alpha?
This P alpha, this one is the probability is not the W function, but the Sudarshan function. So the Sudarshan, the Glauber Sudarshan, yeah, exactly. And both negativity of the Wigner function and of the Sudarshan function are indicators of non-classicality in the quantum states. And they have different threshold times of transition from quantum to classical. And interestingly, how do they depend on the size of the cut? The size of the cut is really how big is this superposition, how macroscopic is indicated by this parameter alpha. In some cases, for some of these indicators, you will see that this threshold time is completely independent on the size. Okay, they decay, so you lose quantumness at the same time, independently on how big is the superposition, okay? Which is completely counterintuitive with respect to what is known. And then there is also something about the dependence of the temperature on the environment, but I will go back to this later on. And now, all these has been obtained assuming a quantum environment, which is a bosonic environment, so quantized mode in a T temperature field. But we can also do the same calculation by modeling time dilation-induced decoherence. So for time dilation-induced decoherence, a very similar behavior occurs. So you have decoherence time as a function of the size of the superposition, and for the Wigner function and the P function, they are absolutely constant as you increase the size of the superposition. So it does not depend on the type of model that we use to describe the environment. Okay. So, final point, the hotter is the environment, the faster is the lot of quantumness. Again, there are indications, another paper. By the way, the previous one, the time dilation-induced decoherence, is the only one for which we don't have an experiment yet. And actually, it's very difficult to experimentally verify that. But then again, here, qubits again interacting with the environment, stationary coherence is present, can be present, at different values of temperature of the environment. Of course, the hotter is the environment, the smaller is the probability of having stationary coherence. Okay, what do I, in the end, summarizing, what does this first part of the talk wants to say? Well, what I mean here, the first message is that the persistence of quantumness in macroscopic quantum systems depends on the properties of the environment, so on the modelization of the environment, but also on the specific quantum property I'm looking at, okay? Whether it's entanglement or its coherence and so on and so forth. Okay, so we have to be very careful, and it is necessary to build models in general in order to make experimental prediction. Okay, second framework, second part of the talk. And here I'm going to give a very specific example in the context of quantum biology. It's a very well-known quantum biological system, and this is the so-called FMO complex. FMO complex is a complex extremely well studied, and it's really one of the prototype examples of quantum biology in which there is evidence of quantum effects in a specific transport process going on within the FMO. I will describe it soon. So it looks sort of rather complicated to be a quantum object. It's formed by 3 protein pigment structures, and it turns out that what happens within this structure is the following thing. Experimentalists have been identified 8 different sites or 8 different dimers. What happens is that you can excitations, when I talk about excitation here, is really one photon, is one energy quantum, is injected in the node number 1, and it propagates, and eventually it reaches node number 3, where it goes to the reaction center. This is a photosynthetic process, so photons are transformed, they go here, and then they are transformed into electrical signal. And the question is, does quantumness play a role in the efficiency of transport? This has been extensively studied. And how is this problem assessed in practice? Well, what people have been doing is building a model of the following type. This is an effective model. Remember, we started from all this mess here. We went into something where you can identify 8 nodes. And now we simplified further by giving a coarse-graining description of the dynamics in terms, you see, of these 8 nodes. And these links in this graph are just given by the values of this matrix. This matrix basically contains the energies of each dimers of the 8 nodes and the couplings between them. Okay, so if you see a thicker line here, it's because it's a larger value of the coupling, and so on and so forth. And the scale is given by this. So this matrix is reflected into this graph with, of course, certain weights. And now you think, how can I assess whether there is quantum transport in this system? And this is what they do. What they do is to this is so-called, in physics, we call it a Hamiltonian of the system. And if the source is number 1, if I inject one excitation on node number 1, then this will propagate according to a Hamiltonian, which is a hopping Hamiltonian. So basically, you have hopping certain transitions, which are quantum transition from 1 to 3. So this is the Hamiltonian of the system, where this sigma minus and sigma plus are the creation, are the lowering and up and down, sigma plus and sigma minus operators. So inversion operators for the 2-level systems, okay? And these GIJs are these numbers. These come from experiments now, okay? So this is an experimental, yes?
So is there an asymmetry assumption? Because it looks like the matrix is symmetric, right? So it's assuming that one's, I'm not sure how to interpret the connections here, but if 1, let's say, inhibits 2, then 2 also inhibits 1, or is it meant to not be a causal?
This comes from experimental data, so from spectroscopy, so it is just derived. And
so
the way in
perfectly
which,
symmetric. Yeah. Okay, all right.
Mm-hmm. So I mean, this is what is given from the experiment. Yes.
I'm just wondering what do the numbers include? Do they include?
It's remarkable that it's symmetrical.
Okay, it's symmetrical.
Mm-hmm. Okay, and then what do you do in this case? So how can you model the dynamics in this case? And in order to proceed further to model dynamics in this case, I have to say that what happens in practice is that this system is, of course, subjected to noise. We have developed a model of noise in this FMO system, which I will explain immediately. And the important point is that, so here I have like a simple drawing. It's the same graph as before. But now I want to include a description of noise which has both quantum features and classical features. So I have collisions. This is an effective model. When I talk about collisions, don't think that this is really microscopic collisions, but it's an effective way of describing an environment. So I have collisions with other qubits, for example, or other quantum systems, according to a certain interaction Hamiltonian, which is described by this unitary here. And then sorry?
I said, where is it, mathematically?
You mean this, when it is described? I didn't write it explicitly.
Oh, yeah,
I can write it, if you want, I can write it on the board. It's just...
Well, maybe you should
I will do it later on. I can describe it in the board. So, but it is a signal... Well, I will say it later on if you want. And then, however, the collisions are not let's say simply, they are random, but they are described by this variable distribution. So this is the probability density for the interval between two consecutive collisions on node I. And in particular, you can have two parameters, which are very important because they allow us to switch between different scenarios. This parameter here is a temporal heterogeneity. So it tells how the collisions occur. When k is small, you have just some burst of collisions. When k is very large, you have very periodic collisions. When k is in between, this is like Poissonian statistic. Okay? So I change k, and I change the statistics of the collision. This other parameter is the spatial heterogeneity, and it tells me how the ancillas hit and collide with the individual nodes in a way that, for example, it tells me if mostly node number 1 and 2 are affected with respect to the other. So it's really spatially changing the way in which collisions occurs. Okay? Very well. Now, in order to benchmark these dynamics, I need to compare it with something which is the fully connected graph, which is very well understood in terms of transport. So if instead of having links with the weight given by the experiment, you have links which are all the same, so that the connection is all the same links and all the same on-site energy, what happens is that energy transfer is very strongly suppressed. So in these quantum systems, if I inject one excitation here, the probability that it reaches the sink is very, very small. And this is due to the fact that if I write explicitly as a state, a localized state, as the state of the initial excitation in one of the nodes, his overlap with the state of one excitation in the sink is very small. It's a way of saying really that interference or destructive interference between the different paths plays really a non-supportive role in this case. It doesn't help the transport in the molecule. And this is one famous New Yorker illustration of interference, in particular among different paths. So in this type of complex, like the FMO, the absence of noise is bad for transport. Okay? It looks as if quantumness plays a role, but at the same time, you need to have noise in order to enhance the probability of transport, the performance of the FMO. Okay, so there is a subtle interplay between the two, and I will show you what happens in the FMO very, very soon. But the first things to note is that the same thing that I mentioned for the complete graph, of course, happens for the FMO, even if the symmetry is partly, it's a less symmetric system with respect to the complete graph, but still the same inefficient transport occur in absence of noise. Well, what happens in presence of noise? Now, for the complete graph, in the case of spatially homogeneous noise, so you have collisions everywhere in the same nodes, you do have a performance which is dependent on the collision rate. So there are certain values of collision rates and certain values of types of collisions, for example, the periodic case, which is ideal in order to have optimal performance. If I change the heterogeneity, spatial heterogeneity, what happens is that if I hit only the injection node, I will have a higher, overall higher performance in the transport. And of course, also in this case, it depends on the collision rate. And on top of that, there are some sort of dips. So I'm able to reveal certain periodicity in the dynamics, which simply come from the fact that, well, this is a finite system, injection starts here, but there will be some finite time in which the state will be back into the initial injection side, and if I keep hitting at that time, I will not do anything to enhance transport. It's very well understood, the dynamics of this system. So best performance is in the case in which I don't hit at all the nodes at the same time, but I only hit the sink. Okay?
Sabrina,
Yes.
did you specify what the noise is?
Yes, the noise is precisely this model that I mentioned here. So in particular, so the noise is
Is lambda or is it,
this lambda here.
is that the,
This
is that
one
the
is
noise? Is that what you call the noise?
no, the noise is a collisional model in which ancillas, so basically other two-level systems, for example, hit the nodes.
Right.
And they hit them with a certain statistics. So the probability of hitting the molecules is given by this actually, and then you use this and you change these parameters.
So
So
what
you
you call high noise and low noise, what is that then? What is then high noise and low noise?
it's collision rate. Look, I show you again. So the probability is given by that one, and here you have the collision rate, so the rate of collisions.
Right.
And you have performance is the performance of transport,
Right.
so the efficiency of the transport property. And you have different plots here. So the efficiency of the transport depend on the collision rate, but it also depends on how, let's say, on the how temporal heterogeneous is the collisional process. And for example, in this case, well, it doesn't, this is the FMO, it doesn't change much, let's say, for different, okay, there are some changes, but you see, you have the optimal performance for certain collisional rate independently, more or less independently on the time heterogeneity.
Right.
And on the other hand, if I now look at the case in which the collision is only on the initial site where I inject the excitation, this performs much worse. Okay? So it seems that for the FMO, the best performance is in the case in which collisions happen everywhere, at all nodes, they can have different, let's say, different statistics of the collision rate. Now, at this point, you can ask, okay, nice, this is a model I can use to predict things, and in particular, I can ask, is the structure of the FMO the result of an evolutionary process which drives the system towards an optimal performance in noisy environments? This is just a model, okay? But you can think, is this the result of evolution? The links that we observe experimentally are the result of evolution. Is there meaning why they have these values, or is it just, random? And the way in which we assess this is, of course, by modifying the hopping strengths. So if you think about this, this is again given by experiments. But if you think now of, for example, reshuffling randomly these links, you might ask, how is the performance of the corresponding transport process. And this is what we do in this graph. So, and in the orange line, you see the case of reshuffling. So we have a probability density of different reshuffling and compare them with the value of the original model, that is the one obtained by the experiment. And you see that actually for the case in which we do not optimize the model, it doesn't seem really that we can say that these values of the links, so these values of evolution are particularly advantageous, because you can find about 40% of randomly reshuffled links which perform better actually than the one of the experiment. So I wouldn't conclude that there is any optimal performance in the way in which, by measurement we obtain this topology. On the other hand, if we optimize the noise, so if we optimize, because we have, of course, parameters, we can run some genetic algorithm and find the optimal noise for the transport. And in this case, it seems that actually the specific configurations of links seem to be actually optimal, or at least reshuffling only about 9% of the reshuffled topologies perform better than the one of the FMO as measured by the FMO. Okay, so take-home message of this part. There seems to be an interplay between the role of quantumness and the decoherence property, but also what I call the geometry of the biological complex. But with geometry here, I mean really topology. So the topology of the network, of the graph underlying. And my claim is that models are very useful to understand and explore the microscopic origins of phenomena like transport in FMO. Okay, now the last point I want to make has to do with a very recent experiment of a quantum simulation of propagation in fractals. This is the reference. It's a reference of, really, I think a couple of months ago was appeared in Nature Photonics. And I was really, 2 weeks ago, I was having dinner with Christina, who is one of the authors, and we were discussing about the potential implications of this experiment. So I want to describe you a little bit what this does. So what you have here is a set of waveguides, okay, which are arranged, so they are engineered in a way to reconstruct a fractal structure. So here is the Sierpinski triangle, okay? And what happens is that they inject single photons here. The photons propagate along the waveguide, and however, it tunnels. So there is certain probability of tunneling to the nearest nodes, okay? So what happens in principle, in practice, is that this initial propagation you will experience, of the photon, will experience some diffusion properties. I will show the experimental results soon, okay? So again, how do you describe, how do you model this phenomenon? It's the same as what I showed before. It's a continuous time quantum walk, okay? It's hopping between nearest neighbor sites. Again, it's a very well-known model which describes time evolution in different systems, only that with respect to what we did before, the topology is different. This is a fractal topology which has been engineered to study specifically.
But you're doing individual hopping here.
This is the Hamiltonian. So what you do is that you inject here, this is transversal, you inject here, it moves along the line, but then there is hopping among these sides. Really the lines identify precisely where there is probability of hopping according to this Hamiltonian. Okay. And here is what you observe. First of all, what you measure is the so-called mean square displacement. So you start from here. Actually, of course, they also study different types of inputs, so where the input is located in other parts. You start from here and you study the mean square displacement as evolves with time. You will observe something like this. So these are different times. As a matter of fact, you will not see, but if you were able to see, these are actually lengths. And the reason why this is a length and not a time is just because they use, because the length is equal to Vt, where V is the speed of light, okay? But in the medium, of course, but it's the same thing, okay? And you see the injection is here, and then it starts diffusing, and it continues diffusing, and I will tell you what they find out in a moment. So what they observe is that, of course, first of all, as expected, fractality leads to anomalous diffusion, okay? With respect to the regular lattice, so the mean square displacement for a regular lattice would scale linearly, okay? In this case, with time, of course. In this case, you find anomalous diffusion, and interestingly enough, this anomalous diffusion allows you immediately to deduce the fractal dimension of the Sierpinski carpet. Not carpet, but triangle. They also study Sierpinski carpets, but not here. So this is the experiment. These are experiment and simulation, okay? They match, so we can just focus on the experiment because really they show the same thing. So you start, and what do we plot? This here, so this mean square displacement as a function.
Have you got an experimental fractal somewhere? What do you mean by experiment? I understand the theory.
No, this is an experiment in the sense that this has been done in an experiment. So what they
actually construct. Sorry.
They've constructed. Yeah, they constructed. These are just waveguides. Okay, the waveguides.
No, sorry, I understand. Yeah, okay. Sorry to interrupt.
This is an experimental result because then they measure. They have these CCD detectors at the end. Of course, they have to do. I will explain it later if you want how they detect it. They have to cut the waveguide of different lengths in order to reconstruct these different probabilities at different times. But never mind. So what you see here is that initially this starts. So first of all, this line would be in the standard lattice. This is the linear. Z is equal to Vt. Okay. as I said before, this is displacement in millimeters is just equal to time. It's proportional to time. V is the speed of light in the waveguide, right? Linear is the case that you would expect from lattices, standard lattices.
Classically.
Classically, but also quantistically, you know, in the same way, both classical and in quantum. So what you would see
You get also.
Are these tessellations?
initially, yes.
These are tessellations you're talking about.
Sorry?
Tessellations, regular.
Yes,
Periodic
exactly.
lattice.
Yes, periodic lattice, exactly. So what you would see here is that it starts with a different behavior, but eventually, again, here is the exponent, but eventually here, when it reaches the first triangle hole, and it starts to, the slope changes, and when it starts to go around the first triangle hole, it starts to take a new slope, the exponent of which is the fractal dimension of the crystal. Okay, so it doesn't need to see the whole fractal to learn that it is a fractal. Okay, so it just needs to go a little bit around to feel the borders of the first hole to somehow notice that there is a self-similar structure. In a way, it's quite surprising. Not amazing, but surprising, might be surprising. And okay, this is intriguing because you can control these specific experiments by building different types of topologies. Of course, only planar topologies, but you can, yes.
Why does it seem like on that fifth diagram there at the bottom that it's attractor stating in that middle spot? Yeah. If it's diffused, why is that happening?
I have absolutely no idea.
It seems strange, right?
Yeah, I mean, it is. Okay, one thing to mention is that after this point, so more or less at this point, of course you have all sorts of finite effects.
Sure.
So you will go back and you will have some other constructive
maybe it's a moment in
interferences.
time, but it looks
So
a bit
maybe,
strange.
yeah, it does. That's true. Yeah. So another thing, obviously, also another thing to mention, but maybe this is obvious. I mean, clearly these dots here are obtained by statistically, so you have to make many experiments, obviously, and then or different lengths, but it is true. It's some sort of quantum interference due to the fact that the propagation maybe goes back here. But it is predicted by it really. If you look now, I don't have it. This is the real experiment. If you look at the simulation, you would see it as well. So it is not an artifact of the, not neat experiment.
No,
it's just what
just interesting artifact.
Okay. And this is what I was just saying, that the interesting part is that you can see the fractal dimension here. And of course, there has been a lot of news about this experiment, and what they say that of course, they believe that this type of experiments might be used. They talk specifically about also the orchestrated objective reduction theory, and specifically about the fact that microtubule, they have a fractal structure, and therefore that you could sort of do some quantum simulations that perhaps can prove the origin of quantumness in these systems. But of course, all this does not assume any noise. And we know that in realistic biological or even neural systems, noise must play a role. And we saw before that actually we need, depending on the parameters of the noise, very many different things can happen. So it seemed to us, again I discussed with Christina, it seemed to us a really obvious consequence to explore what happens when we add noise to this type of dynamics, which is absolutely, let's say, more or less straightforward if we use our own model. We can use actually different types of models, but in particular we can use our collisional model with a different type of topology. So the take-home message here is that in this general framework, really, which is the general framework where we like doing, or within which we like doing models, is you have a certain trigger or you have a certain inputs. You have a photon which is injected in these topologies. Then you have certain dynamics, propagation, something happens, and then you measure. Then you can perform controlled quantum simulations to study phenomena in fractal topologies that might be relevant for biological systems at the quantum level in a controlled way. So they might be useful in order to understand if and in which sense there are quantum effects in biological systems and in the brain. So outlook and open questions. Of course, the first one I already anticipated is, well, can we study the effect of noise models on quantum fractal structures? And it turns out that, well, it's just very simple. We just have to use the same type of approach for the fractal structure, and we can use it in order to understand. What is interesting here, whenever you have a model of noise, understand, I mean, depending on how strong is the noise, you will have a classical dynamics or a quantum dynamics. So you have a way of controlling whether your transport is quantum or classical, because you can change the amount of noise and therefore see what are the difference between the two extremes. And then obviously, I would like to leave you with these questions. The first one is, I would be very interested in understanding what might be a meaningful framework, again, thinking in terms of trigger, propagation, observation, to sort of deduce or postulate some sort of quantum but minimal effective physical model of consciousness in the brain. This should include, however, in my opinion, a description of the environment, even if it's an effective description of the environment, a description of the environment, ideally quantum or a mixture of quantum and classical, but a model, a description, an understanding of how many quantum properties we want to study, maybe more than one. Okay? It doesn't necessarily need to be coherence. It could be that perhaps there is quantum correlations that play a role, quantum entanglement, for example. And, importantly, the role of the topology of the graph. Okay? I need to have a model which has all these three aspects explicitly written. And obviously, okay, this is one of the main questions, what is the role of quantumness if there is quantumness in the process of consciousness in the brain? We know that there are already theories clearly that propose that there is actually quantumness, it plays a role, but is there a functional role? And how to define, how to envisage an experiment to answer to this question. So this is what we would like to do, a flexible, microscopic, physical model to test the interplay between quantumness, coherent, and network topology in biological systems, perhaps in the brain, by means of quantum simulations, even in terms of experiments in this case. And I would like to thank my collaborators in some of the papers that I mentioned before, Guille, Matteo, and Boris. Thanks.
Stuart or Roger? Stuart.
Oh, go ahead, Roger.
No, I just wondered, do you see any connection between your quantum classical distinction to the thing I mentioned in my talk of the classical and quantum reality?
Yes, okay. One of the connections, the closest connection is with the time dilation induced decoherence that we have been exploring. So, but on the other hand, what I say this outlook that I have explicitly written here is precise, and you can read it as, I would like to study this connection. We don't have this connection yet. I think it is possible, and we would like to study this connection. I think this is the next step that to me is very significant and meaningful. Yeah. I mean, we have some vague ideas of some things that could go on, but we haven't yet started. Yes.
Thank you.
Yeah, on the FMO protein, the first part of the talk, the hopping was between, among particular
sites. Yes.
chromophores, which
Yes.
are chlorophyll
Yes.
based, and they're made of pi resonance groups, like aromatic rings, basically.
Yes.
And we have the same issue, with the same thing in microtubules and biology, in membranes, and nucleic acids, proteins, and so forth. So, how important do you think? I think it's very important. So I'll divulge my bias, but that the pi resonance are where the quantum biology is occurring, and it's non-polar, so it's limiting degrees of freedom, and it also may be when the noise comes along, it pumps it in a coherent way. So you have the advantage of being quantum friendly. In fact, in microtubules, we have these pi resonance in one tubule that match up with the next and the next and the next. And so you can get a mesoscopic or macroscopic region of quantum friendly. And we call it the quantum underground. We coined that term in some of our papers. And it seems to be operant here. So how important do you think it is to have these pi resonances? Because I haven't seen quantum biology in any other type of system. Because
Yes.
you have without that you have the charges and the polarity, and here you have nonpolar and uncharged dipole oscillation.
I agree with you. I think it is very important. At the same time, I think that it might be possible even in systems in which this doesn't happen. The key really is to understand how to build an effective model for which I can sort of, which is simple enough, okay, in order to see whether a certain quantum transport that I observe can be additionally modified, or how it can be modified in presence of an effective environment. I think that in this case for quantum biology it is crucial, but I don't think that it necessarily needs to be the only case. It really depends on how well we are able to extract a coarse-grained description of whatever system we are studying, how realistic it is with respect to the measurements that we can do, because this is eventually what we have to benchmark. You know, we need to have some experimental observations that support the model that we are having, and then we need to have a flexible enough model of noise, again effective. We can't, in these systems really the noise is extremely complicated in terms of the microscope. There are so many vibrational modes in the environment, very structured environments, but you can have effective models of environment. There have been really, in quantum science and in open quantum systems, I have a background in open quantum systems, there are very many ways of building effective models which are able to reproduce the same effects of the very complex, real vibrational
But miles of noise, do you mean the noise itself, or the
Vibrational,
heat,
yes.
or whether, or is it the biological structure?
The biological structure, yes. The effective biological structure which induces the loss of quantumness. That is what you ideally would be able to, should be trying at least to be able to model. Because this competes with any gravitational collapse effects, okay? So it may at least.
Or sustains it long enough to reach?
Or sustains it longer. But okay, if we have a model where we have parameters that we can change, we can see actually, you know, for which parameters there is an enhanced sustainment or enhanced, you know, performance or higher performance. And in which cases there is not. But we also need to define what is in the case of FMO, you see, I know that what I'm trying to do is to have a high efficiency of transport. Okay, so I know the goal I want to optimize. So I
These
can ask.
excitons?
Yes, these are excitons. Yes. In this case, in the FMO, is really like a single photon. It's a photosynthetic complex.
How do you define an exciton, please?
It's a photon.
It's a what? Photon?
Initially it's a photon and then it starts propagating, yes, because it performs really, it's a photosynthetic complex. So what happens is that you want to transform eventually light into an electric signal.
Is it an excited electron state?
Eventually this is what in the model, yes, yes, within the model.
Hey, I think Basil and Demis had
I just
questions.
want to have,
and then,
first of all, thank you for this, because I think it's a very difficult problem. The reason why I think that is I work with a group at University College who are trying to deal with the behaviour of single excited helium atoms. And we are finding that blasted thing will not do what we want it to do. So when you've got something like this, who knows what's coming in?
Yeah, I mean, I have to say here, I mean, there is a huge amount of literature on these things. Here, I only cited the paper in which we modeled these things, but I mean, there is a lot of this is like really the test bed for quantum biology. It's really the system which led to, and which in some sense changed, in my opinion, really the perception that, you know, before, I mean, anything which was related to biology was that people would say, no, I mean, come on, it's impossible, it sustains coherence. But in these experiments, I think, changed this point of view.
Well, if there's any advantage to survive, nature will take it.
Yes.
Yes. It's as simple as that.
Demis?
Just a quick follow-on question from this. So if you know, this is going to explain quantum consciousness or something like that, the quantum collapse would have to happen in multiple, you know, thousands of cells at the same time, or proteins at the same time. How do you explain that kind of
I wouldn't.
correlation between all these different, you know, it can't be just one neuron, right? It would have to be whole populations of it. Is that the propagation?
10 to the 15th turbulence for it to happen in 10 megahertz. So yes, I would say entanglement, but maybe another answer.
Entanglement of all of them, that's how it would do it, because you would need a whole bunch of them to
Right.
happen
Yeah.
at the same time
So
for the
that-
thought to be like that, like tens of thousands of neurons.
And I think there is still the question that will be left open in a way is what is being accessed, if you like.
Yeah.
You're really
Yes.
So is that really feasible to entangle? I mean,
Well, I mean,
something
you
messes the
can,
brain.
of course, you can entangle objects at very large distances.
Sure.
These things have been obtained. You can also have situations in which, in presence of noise, entanglement is trapped. So again, a lot of things that we were skeptical about turned out to be, not so crazy. But in order to understand whether this is actually happening or not, we need to know that we need to build effective models that we can assess and benchmark with experiments. And this is in my opinion, the final message is really, I believe that this is what is needed at this point, because we do have already very beautiful theories and ideas on how these things could happen, and we need to bring them one step forward, which is closer to really these physical descriptions. By the way, there are a lot of quantum information tools. I didn't mention that there is a huge amount of quantum information tools that have been developed for quantum technologies that can be used, in particular, to quantify information, quantum information. There's a lot of, we can take all this toolbox and apply it to these beautiful and very fundamental problems. Okay.
All right. In the spirit of maintaining some sort of schedule, I thank Sabrina and thank all the questions. Brilliant. Thank you. And I now would like to invite Joseph Almog and Vesa Halava to give the next talk. And I want to say to Demis and Sabrina that I know you'll have a chance to chat later. I think a very interesting question for you guys to talk about is what's the role of quantumness in protein folding, if any? I think it would be very, very interesting. Yeah.
I would like to join
You will be joining it.
the proton folding. My thesis was
It's
on
a very
proton.
interesting, very interesting.
Not knowing the answer.
Get my coffee, you don't want coffee?
No.
Yeah, it's okay. I'm not much needed.
Hei Vesa, yrittäkää pitää tää niinku...
Mä yritin jotain tuolla nopeita.
Yritä pitää tää niinku kompaktina. Sitten lopu happi.
Joo, mä en tiedä iso osa näistä asioista jo
I'm
ikään
just
kuin.
telling Vesa keep it compact.
I'm a mathematician, it's easy for me to be short, but not understandable. Anyway, mä yritän.
Hyvä.
The model have to evolve. We can start from a very simple one, but we will have them to evolve in time by benchmarking with the observation. But definitely, this is something that's happening.
I think that's good. We're almost done. The last two steps of the marathon. Day one, of course. This is an ultra, so tomorrow we continue. Exactly. Running is always free. Joseph, contain the beam. That is my
Self-controlling.
something like that.
He has me as a control unit.
I'm scared of him.
Good.
He's a biggie.
That's good. That's good. We need a motivator.
Yeah.
I'm trying to de-dramatize, so I should apply to myself.
No, don't.
I want to convince you that all of this is not amazing. It's kind of mundane.
No, actually, what you did in your first talk, you made an excellent introduction to our talk, I would say. So it made us it's very, very simple to come in after your talk. So you will notice. So thank you.
He's skeptical.
Yeah, he's kept. Well, you'll see because we have the ones. We will have the good stats also. When you do that, I will be talking about.
Then you go. I'm in a way a warm-up to your models compared to experience.
Yeah, I'll try to keep it compact. I sense the audience is. I'll hurt the cats, and then we go.
Yes.
But inside I'm not sure. I remember when you got the professorship and you were all. You look. Yeah, but you were.
All right, folks. We're moving on.
And you can open the window.
Absolutely. Absolutely. Sorry. Oh, no, I meant with actually the. All right. So, guys, girls, ladies, gentlemen, I give you Joseph Almog and Vesa Halava, who are going to talk about a lot of stuff.
A lot of stuff, yeah.
So, over to you guys.
Yes. So I'll start. I don't have slides or I just will talk. And Vesa will follow with some more technical slides.
You have slides. Just
the
ones I prepared to you.
Yeah. It's going to be a very old-fashioned set of observations. And I want to tie, I think it's nice in the way you see structured it as a workshop, the kind of, you're going to the gym. To basically, I am not a physics person, so I can't comment on what was said after Roger Penrose, but to the Roger Penrose talk, to the Woodin talk, and I think to the forthcoming UC talk about experience and modeling it. And I'm sorry if it came across, Vesa was watching my exchange with Sir Roger in the morning, that it was intense. I'm sorry if it turned out that I'm a spoiler, sort of. I say, oh, it's not amazing and so on. It's not out of lack of respect to the personalities involved, Gödel or Hilbert or whoever it was that thought it's all amazing. But I want to explain something and de-dramatize that Gödel's theorem, and I think something deeper than Gödel's theorems in the plural, the two incompleteness theorems, Skollem's, earlier theorem, are not surprising. They were, of course we can talk about what's amazing, what's surprising. It's a little bit like the insurrection. We now hear every day in the news what was happening on January 6th on Capitol Hill. You can think the insurrection is amazing, but I don't think it was amazing. I think it was coming. It was long overdue and it was in the pipes. And in this sense, I think the Gödel-Skollem insurrection was in the pipes. And we have a tendency to overdo it, I think, and make it more magical than it is. And it's not more for that reason, it's less, I think, when we do that. So, to Sir Roger, you have to take the bitter with the better. I'm gonna talk about gone men, Gödel and Hilbert, but I will be indirectly referring also to some things I think you think. And you can say to me that I'm wrong about this or that.
I may say your talk is amazing at the end.
It could happen.
To still use this adjective for one last time.
Started it.
Yeah, I started it. It would have been amazing if there weren't these incompleteness theorems. That's the point. And maybe we agree about this in a certain important sense. And I think you see sort of nailed it by saying we have experience of reality and models fail to get at it in some way, and maybe essentially have to fail to get at it. It also connects with Demis.
Demis is here.
Oh, it will address in a kind of fleeting way your why can't a Turing machine, can a Turing machine, step up and do it. So basically, my remarks are really just conceptual, no technology, and very simple. It's going to be about the natural numbers where Gödel actually originally operated. But I believe it applies just as much to the real numbers, to the structure R, and to what Woodin here called V, or enough to all the ordinals, to the absolutely infinitely many, that is, the collection of ordinals that does not make a set at all. But we can talk about n, the natural numbers, 0. You had the 1, 2, 3 without 0, right? Okay.
Already skirting controversy.
Yeah.
I have some there.
Oh, I live without slides. I'm from an extinct kind of species.
We watch here.
Yeah, there ought to be some coordination. There ought to be some coordination. So basically, I want to relate by this triangle 3 notions. One is proof theoretic, what's provable in first order PA. This is what's deducible by a Turing machine, if you will. With no meanings, Hilbert-style formal system. What is satisfiable in all models of PA? I'm not, standard terminology is what's true in all models, but I'm skeptical whether it's truth in a genuine sense or just algebraic relation between formulas and models. And then what's true in N? And that's true for real, true in N. For instance, 2 plus 2 is 4 is true in N. Every, is the numbers of a square, sum of 4 squares. And Goodstein's, these are things that are true in N. Okay. And the incompleteness theorem is usually presented, and correctly, as a failure here if, it happened for predicate logic, for first-order logic, for instance, to be a valid formula true in all models, that's not provable. That would be a scandal. The truth is that what Gödel was working on was on this relation. He didn't have models at all at the time. He actually came up with formulas that are true in N that are not provable. And I want to focus us on this relation, of the relation between truth in N and truth in all the models of PA, some underlying theory. It doesn't even have to be an axiomatic theory like PA. Skolem had the result that if you take the first order sentences, so that's not a deductive theory, just the sentences formulable in a first order language that are true in N, you can always extend this N, the 1, 2, 3, to a model with new entities that he calls alien intruders, A1, A2. These are non-standard integers such that each one of those has finitely many predecessors, but those have infinitely many predecessors. So obviously it's not the natural numbers, even if they satisfy the same first order sentences. And I believe that the deep source of the Gödel phenomenon had nothing to do with formal systems. We can cast it without talking about formal systems. I also believe this is true about eventually the truth. I believe that Woodin is on the right track and the continuum hypothesis is right and is correct, is true. And this will have to do at the end of the difference between truth in the real numbers, how many real numbers there are, maybe determined by ordinals, as the V equals odd axiom suggests, and truth in all the models of real number theory, which is quite a different notion. And similarly about truth in V, but I'm not now going to talk about this. So we are all in the natural numbers. In a way, the natural numbers, though very simple, are a kind of like reflection or capsule of all these deep phenomena, even though technically things get very hairy when you go up, as Woodin laid out today. So what is the problem? The problem is semantical rather than deductive or proof theoretic. The way Hilbert and Gödel cast things, and you have to understand that Gödel was a graduate student in Vienna in a certain ambiance and was trying to respond to a certain zeitgeist that of Hilbert, the school, the Göttingen school, von Neumann, and all these people he was interacting with. He didn't even have the notion of a model. He read Skolem, he tells us later, through Hao Wang and others, but Skolem didn't have the notion of derivability, didn't have a formal system. Had models for a first-order language. That was his big introduction in 1922, in Helsinki, actually, the paper he gave the Congress of Mathematicians. And I submit to you that the heart of the incompleteness, that is, that there's a sentence that's true in end, that's not provable by some formal system, that's a surface phenomenon. The heart of it is in the incompactness. Incompactness now, so two ways of going at compactness is a semantic phenomenon. It has nothing to do with formal systems. So Hilbert might not have existed in this respect. So you have a set of premises, sigma, something follows. In all the models in which this is true, that's a logical consequence in the semantic sense or model theoretic sense in all the models. This is true, this is true. And compactness says if this is the case, there's already a finite subset of this from which this follows. So you can always finitize. For any infinite set of premises, you can get a finite set of premises that's enough. Of course, at that point, it's very natural to try to write a deduction, because a deduction is a finite set of sentences. Another way of getting at compactness, and that's very important because it puts us on the road to expressibility, to the power of the language to express certain notions, is that if a sentence of the first order language in question is true in arbitrarily large finite models, that is, it's true in a model with one thing, two things, three things, and so on, dot, 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 it's inevitable it's going to be true in an infinite model. And that's a theorem that's proved by compactness, namely the first order language, in particular of PA, cannot separate finite models from an infinite. It does an overspill to infinite models. And of course, let's call him knew that. Now, I would say something even stronger about the mundanity and inevitability of incompleteness. I was just talking to you about this, giving him a letter that Richard Dedekind wrote in 1890, before Stalin, explaining his modeling of the arithmetic of natural numbers and saying, you know, the hardest problem here, so he's writing to a schoolmaster, so he's not being technical, the harder problem of modeling n is how to cut these guys, the alien intruders. Because I have to use finitely many. And I can't use finitely many. God knows why he thought he can't. But he had a theoretical project, which was inherited later by Hilbert, that finitely many is arithmetical, and the foundation of arithmetic should not be arithmetical, but should be set theoretic or logical. This was very popular at the time. At any rate, there's a circularity, because if you introduce finitely many primitively, finitely many defines what natural numbers are, and to say what finitely many is, you have to use, you know, mappable into some number, natural number n, and you're running in a circle. You understand the natural numbers in terms of finitude, you understand finitude in terms of natural numbers. And that sent him trying to understand the structure n in terms of arbitrary subsets, in terms of a foundational language that doesn't involve that, and that involves problems that you talked about today about arbitrary subsets. I don't want to go into this, but I want to stress that in a way the non-standard models, the threat of the non-standard models because of the weakness of the language, is the other side of the fact that we get completeness for first order languages. That is, the logic is complete so that if something is valid, you could prove it. And that's why, because you're not trying to prove very complicated statements, because you have emptied, you vacuumed your language from notions like finitely many and so on. That's why I said that when I said to Sir Roger, here's a logical consequence that's very easy. You know, there are at most finite, at most 25 people in this room, therefore there are at most finitely many people, but we can't write this in a first order notation because of compactness. So, I would like to suggest this, and to allow my friend Vesa to come in, with some example, he's going to talk about Goodstein. All of these examples have compactness as the sort of, the big alien Godzilla sort of, in the back. So it's from compactness to completeness, and from incompactness
to incompleteness, according to this diagnosis. Compactness, in some sense, is the question of whether our language of thought here can make the distinction between finite and infinite. And it's a big thing in the back room of these discussions of Gödel's column and so on, that in some sense they've adopted Hilbert's program, about which already Poincaré complained, that in some sense Hilbert talks about finitary system and finitely many symbols, and a proof is a finite sequence. But in some sense, the system doesn't understand this notion from inside of finite. It doesn't have this notion of finite. We, from the outside, see that it's finite, but it's not expressible in the system that so-and-so is finite. I mean, you can write a condition in first-order notation that there's 17 things, but not that there are finitely many. So, now rounding up and leading to you, what I wanted to say is, let me give, how am I doing in time? I don't want to...
You're doing well. You
Okay.
have to bring infinity in.
Okay. Oh, I brought already infinity by bringing the finite. The infinite is the infinite.
Yeah. Exactly.
But let me give another example of this, how expressibility, what you can express in the language, and whether it's allowing compactness theorem or not, independently of proof systems altogether, is a passepartout. You know, it explains a lot of things. So here's a great logician, Saul Kripke, who is in the camp of Sir Roger about these matters of mind over body and so on. And he says to us the following. Okay. So this is the question. Saul says at some point that the famous Turing thesis that all effectively functions, calculable functions f are Turing computable, so let's call it Turing computable f, is really, for all the jazz, is a corollary of the completeness theorem of first-order logic. And I think he's correct, modulo one premise that he doesn't quite get into. So what's the argument? It's very simple. So f is calculable intuitively in mathematics. Let's call it humanly what's Demis? Humanly calculable, not artificially. Okay, so Saul says this means that there's a logical consequence relation, there's an argument in first order logic that encodes f. So let's call it f star. It's some argument in first order logic that's model theoretically valid, that in all the models of the premises, basically a calculation is an argument. It's an old idea of Leibniz problem. Now, completeness theorem of first order logic, Gödel. So we get that it's provable in first order logic by a finitary proof without meanings and models that star. And now by Turing, we get that whatever is provable in a formal system is Turing computable. There's a program calculating it. So we've gone, assuming this, we get the connection here. Okay, one parameter that Saul Kripke mentions, but kind of poo-poos as obvious, and that's odd because he's, unlike other logicians, he's very philosophically astute, is that this relation holds modulo what he calls Hilbert's thesis. And what's Hilbert's thesis? Hilbert's thesis is that every natural mathematical argument that Diophantus or Andrew Wiles did, because remember, Andrew Wiles did not do a formal proof in some formal system. He was in Oxford someplace or in Princeton someplace doing natural mathematical English arguments in number theory. Every natural mathematical argument is first order expressible. We can write formulas such that the premises logically, model theoretically entail the conclusion. Okay. And that's, at the very least, as contentious as this. Because, as I said, there are many natural arguments, I would argue, of mathematicians, including the words finitely and infinitely, that are not expressible by first order. One of these arguments, I think, lead directly to the Gödel thing, and that's why I repeat, it's not such magic. You know it's coming. It's the argument that I mentioned today. Tarski knew about this even before Gödel, and of course Skolem. So this is an argument that has infinitely many premises. 0 is F, 1 is F, 2 is F. You might say it's the kind of nascent primitive form of induction. Not for induction in first order notation, but the 2 infinitary induction. If you've got it at 0, you've got it at 1, you've got it at 2, dot, dot, dot. You've got it for all the numbers. The problem is that this is a not compact argument, because it's not true that you can center on a finite subset and it will give you that. You need the whole fucking thing, as it were. And of course, non-standard models are going to be such that 0 has it, and 1 has it, and 2 has it, but the alien intruders don't, and it's going to kill this. But the model doesn't know from inside. We know from the outside, but the model doesn't know it. I think you're going to talk about the theorem of Woodin, where, you know, we know from the outside that some function is not computable, but in the model, if you define in the non-standard model, it is computable. It fakes itself as computable. So one can, you know, babble about this for quite a bit. I'm receding, as I promised you, see. I think that this, let me make a kind of conjecture, conceptual conjecture, it's not a mathematical conjecture. That behind, this is not due to my own thinking, I kind of formulated to myself as a student when I was young, and talked a lot to someone now dead, but very, very intelligent, Georg Kreisel, in a way was making this, going through Gödel, Skoll, and he knew all these people, of course, and was essentially making this point. It was very hard to understand that this is what Kreisel was saying, because he wrote in a horrible way, very complicated way. But this was his idea. The idea was that in some sense, throughout all these limiting incompleteness results, in the back of them, as I repeat, was Skolem's idea that truth in set theoretic models, whether it's in the natural numbers or the real number theory, or he of course talked a lot about axiomatic set theory, does not get a truth in the universe, whether the universe as a whole or fragments thereof, that are not models but are reality, so to speak. Kreisel's idea was that in all these cases we have a version of what's called Skolem's paradox. Skolem's paradox famously looks at Cantor's proof that there are uncountably many reals. So there's more reals than natural numbers, and Skolem produces denumerably models with denumerably many entities. Essentially, let's call them the natural numbers, but the same. Denumerably many things, obviously not all the real numbers, where this theorem of set theory is holding. How could this be? There must be more. And of course, what's going on is very similar, in my view, to what Woodin's theorem is into, that inside the model, you know, what's expressible is different from what we, in our incompact background language, see is not true. There aren't uncountably many things, so to speak, absolutely in Skolem's denumerable model. But the model thinks there are, because some function is not 1, between two representative, the natural numbers and the real numbers. In short, what I want to say is, when you tie your hands behind your back and you don't let yourself express natural mathematical discourse because of some ideological project, which is that we will be able to prove all of this by finitary means, in strings that don't express the meaning of finitely, don't be surprised that you get bitten. And in this respect, it doesn't, of course, take away from the greatness of Gödel and Hilbert and Skolem and all these guys. I mean, von Neumann put the consistency, the unprovability of consistency in 1 month when he heard the first incompleteness theorem. So all these people, it's not an attempt to say they were not clever. Of course they were clever. But in a way, we set ourselves into these incompleteness phenomena by restricting the expressive power of the language, and what I call incompactness, should have been reigning, and we deprived ourselves of the borderline between finite and infinite. And more on this, Vesa, you should slide in with some more examples of this.
Okay, so I had slides for him, but as usual, he skipped them. But anyway, the point was here. So we think that Gödel's results are essentially about the non-standard models, which he already explained. Then I skip the hard part and start my part. So I'm a mathematician. I would be probably a computer scientist in everywhere else, but in Turku I'm a mathematician. I know something about computation. I don't know anything about mind and matter. No, please, I don't know anything about it. But I can talk to you about computation. I separate two computation, actually in vein of what Joseph just said, but I use different words. Mathematical computation for me means that I'm doing mathematics in N or R or V or whatever, in the structure where the mathematics is done. And then there is formal finite computation, which is done by algorithms, Turing machines. It's formal, it's done by the rules, the algorithms. And finite, we usually assume that algorithm stops, they terminate. Of course, we can skip that rule and make it more efficient in a way to model something. I'm not against that, but everything here is about formal computation by a Turing machine. And we know that formal computation, as it's said here, it's connected to the formal probability by Gödel and Turing. So it's possible to do the computation here. But Joseph's picture is very good. You are doing it actually in all the models. And now we are showing what is computation in models, in one particular model. So the compactness of first order logics, for example, this is a first example. As Joseph already said, so there's a Woodin's theorem which says that every function, even non-computable functions, they are computable in some model. So there exists a model of PA where whatever function is computable. And actually there is one Turing machine that computes all the functions. You just change the model. And the Turing machine is very simple. It prints 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, infinitely many times, all the numbers. And you can choose the model so that it prints your function. And this is because the first order logic is compact. So we have a model for every finite fraction of a function. We get a model for the whole function. But that doesn't happen, not even in a formal computation. So you can give me a function, any finite part of it. I can make a short Turing description that it prints for 73, it prints 7, 52, it prints 8, and so forth. But that doesn't mean that the whole function becomes computable in the standard model. Because Turing machine actually works on strings. Words in Turku, automata way. We talk about words. But in strings of symbols.
Words without meaning.
Words without,
sure they
yeah, words without meaning. And there is no real natural compactness, as Joseph said, as is here, in the Gödel sentences. And the same thing. So that's something. If you model, something comes in. And these are these non-standard models which sort of do something that the model doesn't know it's non-standard. It still contains numbers. But the successor function, sum, so forth, they are completely non-computable for non-computable function. They are not recursive. So the successor, sum, they are something different. Okay, so then Joseph already introduced finiteness, infinity problem, or okay, let's call it problem in mathematics, in first order logic. So I show you a few examples of infinity. So actually unsolvability, undecidability always means that you have to show something unsolvable, you have to show that the task is infinite. It's usually done by reduction, but that's the point. Because with finite, you can compute something that if you prove something solvable or decidable or computable, you actually prove that the task, although the set of instances is infinite, you can finitize it into some finite fractions where you can do the decision. Yeah. So infinity is in. We are able to prove unsolvability in some problems. So I have two examples of infinity in computation, and the first one includes
proving something unsolvable, undecidable. So the models don't help. In case halting problem, so everybody knows what the halting problem is. You are given an algorithm, asked whether it or Turing machine with an input, and the question is, does it halt or not? We can define in first order logic for a given Turing machine, a given input W. We can set a property formula which says that this M uses at least n steps on this input W. And I can say that this computation is finite in natural numbers. I can say that there exists an upper bound x such that whatever number of steps the machine takes on W, the x is the upper bound for that. But the problem is that I can't say this in all the models. I can say it in the standard model, in natural numbers. This means if there is a natural number, it means that the computation is limited, it's finite. But although we have, let's say that we have a non-halting Turing machine M, it means that this here, the negation, is true in a standard model in natural numbers. There still is non-standard model where there exists an upper bound, which is actually an infinite number. But the model doesn't know that it's infinite. So we can't prove because we can't get all the models. Use this. And that's why the non-expressibility, or that we are not able to define finite, it brings in something. So you tie Turing computation with provability, first order logic. It's good. They fit perfectly together. I'm not arguing against that. But then the unsolvability, undecidability has roots in the expressibility of finite. And then the last example, which I thought would be surprising, but already in the first talk, my surprising part was spoiled by Sir Roger. So Goodstein sequence, this is a nice example. I have an example of something here also. So you already know, you are familiar with the sequence. It grows very, very fast. And the thing is that we can prove that every Goodstein sequence terminates to 0. Okay? If everything stops at 0, we can compute the function which gives the minimum number of steps, minimum number of non-zeros in the sequence. That would have been surprising, but not anymore, I know. So that is something. So we can do this. It was mentioned already that this theorem 1 cannot be proved in PA here. Why? Because there is a non-standard model where this doesn't terminate. That's why there's no provability, which means that, well, we need something else. And what we need is infinity. We need the ordinals. The proof is not difficult. So you map all these numbers, just replacing the least infinite ordinal omega there on the base, for the base number, and you get a decreasing sequence, which terminates, which means that also the sequence terminates, the original sequence. That's it. So that was my part. I tried to show that the role of non-standard models, role of can't express finite or infinite, computation tied in the first order logic brings these issues, and they are visible through non-standard models. And as I said, I don't have a conclusion slide here, because when I have one which says something about mind, Turing machines, what happens is that we get to a 1 hour discussion about mind versus machine. That's something, as Sir Roger said, that can be taken outside, and I'm not coming. so yeah.
Thank you, Vesa. And Joseph.
Do you want to conclude? Okay.
I have a question for Demis and Vesa, which is that, so do you think that this can be done on a Turing machine, what Vesa is talking about? Or Vesa, do you think that, so do you sort of see the question? Is there something going on here, Demis, that you think that could easily happen on a Turing machine, And I'm not now saying in the way that we might not invent another machine that can invent Turing machines. In fact, later on I'll try to say something like that.
Look, I'll say a bit more about this in my talk tomorrow, but I think that the point I'm making is if you're going to say a problem can't be done by a Turing machine, I think you have to be very precise. Like, what about the problem is it? That is the key thing. Because it can't just be because it was hard for a human to do. We've proven that many times over. That's not a good measure of whether a Turing machine can do it or not.
How about, Demis, how about that the Turing machine doesn't understand it's finite?
And then, well, we'll come back to that. Then the second thing is, then if you're going to say, okay, there is something special. So this is the bit about the problem that's difficult for a Turing machine, and we have to explain why. And then you have to explain what you think in the human brain is going on that's special, and commit to that. Which obviously Roger and Stuart have a proposal, which is the quantum consciousness proposal. We can discuss about the proof for that or not, and then but when you say that, you'll basically have to commit. What you're really saying, I think, in the limit is there is some special extra thing the brain's doing, and so I don't think you get away. I don't think there's much space in between.
I totally agree.
For that, agree. That some problems really hard, that too hard for a Turing machine, but there's nothing special going on in the brain. Then I don't see where that space is vanishingly small now. I think one could have argued before that was quite big, that space. But I don't know what's in that space.
I have a question, not a remark. It's to you, Woodin. Can you say how you read your theorem? Because we've had infinitely many discussions about what your non-standard model theorem is.
So I should say a precise statement of the theorem that I proved. And it was a commentary, supposed to be a mathematical commentary that the question of free will makes no sense. And so the theorem is this. There's a specific Turing program. And I'm going to reference this to piano arithmetic, but you can do it for other theories. So take any model of arithmetic, and this program computes what the model thinks is a finite string. Okay? It may be nothing. It may have no output. In that model, lengthen that string however you want. Then you can extend the model, like extend time, and in the new model, the output is exactly what you specified. So it would be like, in the world, imagine you were running this program. Let's imagine that physics is first order. Pick an outcome of an experiment that you think can't be computed. That's a finite string. Now I extend time into a non-standard model. We can't tell that. But in that new model, this program which I showed you in advance computes as additional output exactly the thing you said was not computable. And I show you the program in advance. So and you can pick any extension you want. So does that mean they're non-deterministic things? In other words, to say that something's not deterministic, you have to put a space bound or a time bound on the length of the computation. That was the only thing I was trying to make. So it's kind of a surprising fact. It's one machine, one program. In any universe, it has finite output. In that universe, extend that however you want. Then by extending time, that same program continues to run and produces as additional output exactly what was specified. So it could be everything you say for the next 50 years. There's one program, I extend time, I get to choose how I do it, predicts what you do. And then we do it again. You say, wait, I want to do this again. I want to act for 1 billion years. Here's what I'm going to do. I say, okay. I extend time again. Program computes exactly the new thing. That's all. It's just a twist on Kolmogorov complexity.
Yes. Mm-hmm. Okay, to be continued, right? Thank you, Basil, Joseph, and I propose a 5-minute break, and then I will promise to be very brief, as I'm the last speaker of the day. So, if that's all right, we take a little. Because it's almost like he does something very clever where he sort of proposes this kind of, I don't know, Faustian tactic. You want it this way?
But put it in a certain way. I don't know.
I'm just going to see if I'm successful with this.
Mutta sä et voi vetää viirtä suoraan tuohon.
Joo.
Sä et voi tehdä sitä. Okay. Pitää vetää se koneen kautta, koska jos vedät suoraan tuohon, niin me ei saada sitä eteenpäin.
I don't want to. Can you just pull it from here somehow?
You want your cable? Yes, please. I'm just so I don't forget. Yes.
I want to do it from here and pull it to wherever you're going.
Thank you.
I'm just going to call you for this.
Sitten voidaan vetää se toimiks toi? No niin, sillä voidaan vetää. Ellei se halua ottaa, niin sitten me kätellään. Suoraan monitoimaan. Toi tikkuinen kohtaa olla varmaan. Tällä tikkuinen mulla on varmaan.
I mean, apparently there was sufficient technological advancement to manipulate quantum systems very well without having too much. But then what happened is that this ability allowed little by little also to have
Assume your positions.
You're chairman and speaker. I'm not sure
I know.
approve this.
I don't either, so that's why it's best to get it over with.
Trouble is the moment you're defining your position, you lose your momentum.
I know. All right, folks. This is the last of the day, so we are soon free to pursue other activities. I think one thing I've noticed so far today is that I think one of the things that we should do one day is we should have another meeting that's just about nomenclature and language. Seriously, it's really, really important. There's lots of seriously amazing insights here between different people, but we talk such different languages. Yeah. It's very, very hard to latch on to what people are sometimes talking about. And I'm just encouraging everybody to take the time to try to figure out what the other people are saying. I'd like to think that there are maybe difficult and crazy, but not nonsensical things being talked about here. So try to invest in trying to understand. But I'll leave that to tomorrow. So today I'm going to talk about something that I've been working on for a long time, which I just really call making sense of experience and the origin of models. So before I really get into the idea proper, I want to say a few things about what I mean by experience. So in order to sort of achieve the goal to begin with, I believe that we're going to need a new conception of reality that kind of reconnects models, things, and experiences. When I talk about experiences, I mean all experiences, not just human experiences, not just in one model. I mean other humans, cats and chickens, and this chair, and a little piece of this table. And here is something funny that immediately happens that's a trap of our language, which I spot out there next, is that experiences are not of things. Maybe that's the case. But the way we talk, we always think of experiences as being generated by some things. But perhaps it is, and I'm going to try to suggest that actually maybe things work the other way around. And there are some very, very interesting benefits to thinking about the world in this kind of conception in this way. So things emerge later through models. Models are really appealing, sometimes confounding, because experiencing them or through them, can often appear indistinguishable from naked experience. All the models that people have talked about here today contain some kind of notion of thinghood. They're things or of things. But there seem to also be experiences beyond the types of models we talk about. So it's not just in the sense of, things like what's provable in a given formal system, but how we really experience things like truth. How do we conclude that we've witnessed something to be true? And the question I'm asking is that might experiences give rise to thinghoods and models? So sort of try to park your other views to one side for a moment and sort of see if this might work. So, I remarked on this earlier today. So there's things like Gödel incompleteness. We've, people much smarter than most have talked about it today. You could sort of think about it in summary that maybe there's truth beyond models. There's halting in symbolic computation. Maybe that's suggestive of something that, as I pointed out to Demis earlier today, that maybe that's something that could a Turing machine come up with the notion of halting on its own? I'm not sure. And then there's just weird stuff in physics. The omnipresence of action principles in models of matter is something that I think many people have found puzzling over the years. So why is it that we have this really amazing principle that seems to be outside of the theories themselves, but actually we can use them to generate the dynamics of all of these systems? Also, there seem to be these different correlative and causal properties in models of matter. So Sabrina talked about now we're finally starting to talk about things like discord, not just entanglement. There's work recently about really starting to think about entanglement phenomena that's post-quantum entanglement. So one question I've been asking is, are these issues related? And I think the answer is that they are. And I think that we need a new conception of reality to capture the key experiences that are left out of these modelizations, but are actually an essential basis for it. So the way I think we often end up talking about this is that people always talk about, hey, we snuck something into the model. But actually the other way to think about it is that, no, actually, we were trying to hug this whole thing, our experience, and something slipped out. So when we modelized, we didn't quite capture the whole thing. And maybe that very point is the key point. So this is then sort of the question about a little bit that when you think about what Sir Roger was talking about in orchestrated objective reduction, it's sort of an access mechanism to something. So is it an access mechanism to sort of some list of models and insights and axiomatic structures that are just given in nature and they sit separately from various conceptions of physical reality we've made? And that might be. Or is there some ultimate model which encompasses all others? And when I say covers now, I don't mean in the technical sense. I mean is in correspondence with, reflects, is isomorphic to nature. Or is there a way to think about things in a way where modelizations have a common origin and maybe they even have a sort of a genealogy and that they're related to one another? And I think I've called that conception something called the manifold of all experiences. And it's a construction that allows us to pose these questions. It allows us to study the origin and evolution of models. And it describes I think a novel generative process that gives rise to all models instead of this is not a deductive or regressive approach that's trying to relate axioms to theorems. So there's really, in a way, one set of axioms that we're going to talk about, so a new conception of reality, the manifold of all experiences. And experiencing it has consequences. And those consequences are generative, and they really, I argue, will actually be found at the bottom of all modelizations that actually we've talked about, even including today. So here are sort of some of the key descriptive ideas. There's lots of math. I chose to not talk about detailed math today, but try to capture the whole idea. There's a sort of a whole telephone book of results, which we can discuss offline with anyone who's interested at all. So the idea is that experiences precede thinghood. The manifold of all experiences contains all experiences, and this is important, including the experience of experiencing. It's not a set, it's not a thing, nor is it an individual experience itself. It's inexhaustible, so there's always more to be experienced. No thinghood, spacehood, or timehood is contained therein. And here's the other key idea, is that the experience of experiencing is limited by indistinguishability. And what we mean by that is that as we experience experiences, and again, keep in mind, not of things, not generated by things, but just now the notion is that there's this new kind of currency that we have, experiences. They can appear similar to us, and the collection of experiences can be unclear. So there's this kind of twofold indistinguishability. One is unclarity about how many things are we precisely examining, and the other is which collections are we precisely examining at a time. And I sort of argue that it's sort of the cradle of action. So how do we do something concrete with this idea? So the way we modelize the manifold of all experiences is by using the fact that we can assume that there are always experiences to be experienced. So we model this as a kind of a sampling process. So we say we can model this inexhaustible pool in a very specific way, and the idea is that the limited nature of experiencing means that while we sample, we might not have this ability to distinguish one experience from another, nor which set of experiences we're experiencing. The way we do this kind of modelization is, in my case, I use something that I developed, which is a sort of an extension of automata models that is structurally dynamic, coupled stochastic automata models that have a notion of indistinguishability that allows us to make these ideas appear mathematically precise. It's important to notice in a way that this process is fundamentally incomplete in that there's always more to be sampled and you're never really quite sure of what you sampled. So different samplings always leave sort of some room at the bottom. And this is sort of one of the important features here, is that the kind of thing that we've talked about trying to get rid of here today, here is something that you can't, you got it. It's here to stay. But I think that's going to turn out to be okay. So in the way, what we're trying to do is we're trying to say, hey, we're going to try to see what happens when I make a mathematical model of the experience of experiencing the manifold of all experiences. And what we try to do is we sort of say, hey, let's talk about now models of matter. So let me try to make a candidate theory of matter with some spatiotemporal structure and some dynamics on it. And the way we do it is we try to set up multiple versions of these automata. And it turns out that when we look at these multiple copies and we say, hey, we were looking at initially one experience, it actually contained a collection. Under what conditions does this indistinguishability become stable? And here now, when you look into the math, it becomes very possible to say, well, under no conditions whatsoever. Or what specific conditions have to be met for this to actually work? And it turns out that under a specific set of constraints, which for now I think we can think about as a set of polynomial constraints that have to be satisfied. And all we're really doing is we're saying, I started with this experience, it looked like a thing to me. I now try to make a model of something temporal and something spatial, and I say that, hey, in order for me to talk about thinghood, at least the structure has to have some well-defined probability assigned to various attributes that it exhibits. You know, but these are sort of present in all physical theories. So interestingly, it turns out that these kinds of models are solvable, and they generate very, very specific results. And I'm going to talk a little bit about the results because the math is very involved. So in these types of models, what's interesting is that something like the action principle is naturally present. So we get models of matter. They're imbued with a dynamic complex value distribution for attributes. So what I mean by this is that in these kinds of models, the idea that properties of matter, for example, exhibit with complex value probabilities is a natural consequence of the idea of the experience of experiencing something in an incomplete way. Unlike traditional models of quantum mechanics, all of these distributions have temporal structure. All of those temporal structures are always coupled to the matter states. And interestingly, there's always marriage to a spatiotemporal model. So there's a sort of a complex that emerges. So you get space, you get time, you get a well-defined model of matter, and it has dynamics. And it naturally has complex valued attributes. They evolve temporally. So in many ways, referencing maybe work of Sir Roger maybe more than anyone here, it's isomorphic to the technical result for totally different reasons. So here really there is actually, the way to talk about it in the old-fashioned sense is it's almost like this, that if you started with many candidate spacetimes and many candidate models of matter, and then you said, do they, under any conditions, does there exist a set of circumstances where we get a stable conception out of these things? And it turns out that there does exist such a conception. What's interesting also is that these things exhibit naturally a spectrum of entanglement and uncertainty properties from classical to quantum. So what I mean is that just by using this process, we can lift out different kinds of models of matter exhibiting classical properties in classical spatiotemporal structures, exhibiting quantum-like entanglement properties. And so there's this work recently, or maybe it's not that recent anymore, but device-independent descriptions of entanglement and quantum mechanics, which lend themselves quite well to thinking about this, where you sort of look at this diagram where you say below this line we have all the classical correlations between objects, and then we have this convex curve above them that describes all the quantum correlations. And then actually we have kind of a triangle at the apex of which are all the non-communicating correlations. But there's lots of stuff in between. And historically the question has been, well, what is that stuff? What are the beyond quantum mechanically predicted correlations in the modes of matter that occur before we actually sort of just go into the non-signaling correlations? Well, actually here we generate lots of models of that. So this is actually something that we should be able to go kind of test. We should be able to see that, hey, are there modes of matter that exhibit these kinds of correlative properties whose statistics are different from the ones predicted by quantum mechanics? We can also exhibit all kinds of uncertainty properties naturally in these systems. So the idea in a way that you have now a physical object that has two attributes that can't be sharp simultaneously is naturally present and is a consequence of this idea of limited experience of experiencing. And interestingly, as predicted by Wim van Dam and some others, the notion of computational complexity actually disappears at the apex of these correlative models of matter. And for that, those guys don't have an explanation. I can now offer a very natural explanation for that, because actually at the apex, there's no longer thinghood, there's just experiences. And like I said earlier, all these models are always naturally coupled with spatiotemporal structure. So we basically sample experience, we're not really sure of the precise boundaries of our sample of experience, but we start with the idea that what if we saw one thing? Could we always maintain some kind of a stable model of thinghood in some spatiotemporal structure that exhibits all the sorts of things that we're familiar with? And the answer is that we can. And there's natural reasons for all of those properties to arise. So far, this is sort of very physicsy set of results. But I think we've already also discovered that models of mathematics and computation also can be thought of this way, and they're not necessarily dynamical. So this is I guess a somewhat radical claim, but in a way the idea now is in a way that, speaking for example earlier to what Hugh was talking about, is that we're sort of modelizing now here what happens, when we're having these kinds of conversations. And, all of that structure that you use, Hugh, for example, I would say that I think it turns out that there's even more structure we can use and exploit. I'm not sure how yet, but there's lots more structure. And the structure we found already now, I think I can relate to, let's say, here now we can kind of ask the question, for example, like, how can we have a conversation about stable symbolic structures? Like, how is that even possible? And then, are the stable symbolic systems necessarily coupled to sets of computation? And I can show that they are, and then you can ask the question of, does that set make for a Turing universal computation? But also now you can talk about things like halting, because that's outside of the thing that's generated is the formal system that we usually restrict ourselves to through a generative process. So if you like, in a way, this is a sort of a physics-like way to think about things. But all models now emerge from this. And now models of mathematics or physics or computation, they're just different modelizations of experience. So, I emphasize that I don't mean the idea that here are sort of models of physics and here are physically realizable modelizations of computation. No, here are models of matter, which are modelizations of my experience of certain aspects of reality, and here here's FPA, and that's Hugh talking about his experiences of some mathematical realities. And actually they're no different. Really the currency at the bottom hasn't changed at all. We just have this collection. It can be sampled in a very consistent way. I'm very much hoping that Demis could build this kind of a machine. And what's very interesting here now is this kind of a thing quantum or classical? That doesn't even make sense to say that anymore. Those are different modelizations. They have huge utility in different contexts. But this is more to talk about the origin of those things. Where are they coming from? How do they relate to one another? And what could we do with that? So here I take the stance that truth is an experience. So we really ultimately confirm by observation. Incompleteness is ever present because we can't completely modelize the manifold of all experiences. So we can make testable, falsifiable conjectures. We can make new tools for novel discovery in math, computing, physics, and philosophy. We've done a bunch of that, mostly on the physics side. So I think I can say now that in a way, all known theories of physics to date, we can generate thusly from a single origin. And what's nice now in a way is, for example, the action principle it's still outside those modelizations, but it's not outside of this one. Because what's really happening here is that literally the experiences that can be wrapped into thinghoods that have well-defined attributes and dynamics actually necessarily also are associated with families of function, which we can write a sum over the spatiotemporal structure that they emerged with and minimize that sum. And yes, it turns out that those are the same as the dynamics that survived the modelization exercise. So it's in fact impossible to make a real theory of physics without those actionable properties being present. It's interesting, I think, to think about what kind of leverage could be gained in mathematical explorations from this sort of extra structure. So my conjecture is that actually all models arise as consequences of limited experience of experiencing this new conception of reality called the manifold of all experiences. And sort of in the spirit of Demis, we can build a model of what's happening here, but it's really sort of a generator of all other models rather than the other kinds of models that have been talked about here today. So in sort of spirit of the 2 days here, I wanted to say a few things about thinking about modelizable and algorithmic insight, those being two sort of slightly different things. So in this new conception, this is all in a way a given. Yeah, we have that kind of insight. I observe that to be the case. In fact, I think the one thing we can definitely all agree on is we all observe that. However we get comfortable with it, we all experience Gödel. We all leverage those results. We all leverage halting. It's just in a way, where is that all happening? So in this context, of course, then, what needs to be explained is the emergence of models with their limitations, and we've accomplished that, with this exercise of modelizing the experience of experiencing and showing that, you have to accept some new ideas here, which is that, mathematics now in a way is inherently also associated with sort of spatiotemporal structures. I should mention here that, of course, the language fabrics that's used to do this modelization of the experience of experiencing is, of course, itself a model, right? So all of this stuff is always stated in relation to a given modelization. And you should think about fabrics as themselves having been emerged from the same process. Fabrics have a neat property that actually they're self-modelizable. So it's a little bit like maybe a generalization of the result that Wolfram had about the idea of universality in the cellular automata sense in the context of cellular automata. So you can apply this process using fabrics to modelize fabrics again. But there are many other ways. Fabrics are not necessarily the best one and not necessarily the most suitable way to do it for all circumstances. I think this gives us a more sort of structured understanding of both the common origin and genealogy of models. Maybe this sort of also speaks to us to if something like orchestrated objective reduction is happening, let's say, in the human brain, well, maybe that's the way in which we access the manifold of all experiences in the context of a given modelization of matter, which is actually not quantum mechanics, it's the Penrosian gravitized quantum mechanics. And I think that's very important and interesting to look for those types of structures in the human brain in the context of given models of matter. But the idea here is that we're not now looking just into sort of a Platonism as an idea that's somehow beyond modelization. It's just another intramodelization scheme. And we're looking into something with a little bit more structure than that. So one of the things I'm very interested in is any kinds of things that can be formulated that I wouldn't be able to capture. Of course, the reality remains that there's very hard things that folks like Hugh are working on. I don't know how to answer them, and I don't know how long my machine would take to try to answer them. But it can I think it can talk Woodin. So does that mean that it's definitely not a Turing machine? I don't know. But I know that it can do lots of these sorts of things. And I'm certainly very interested in any ideas that or modelizations that I couldn't reproduce. So that perfect timing.
It's actually
Thank you.
the chairman.
Yes. Yes.
That's the way to do it.
It's the AI who
Yeah, exactly. And I chose to not put any math in there. There's a whole lot of math. We think it's pretty solid. Yeah.
Could you put in a little math?
Sorry?
Could you put in a little math?
He wants
no,
maths.
I would like a little. No. So you alluded to stochastic cellular automata.
Yeah. So basically, maybe we can take this offline because I know everyone's had a long day. But
okay.
I mean, basically, what you're doing in the way is you're kind of the reason why I call them fabrics is because I'm trying to make a kind of a candidate structure that's not yet committed. So there needs to be some kind of a notion of something that could turn into some kind of a structured set, right? So it should be able to exhibit order relations. It should maybe even be able to exhibit spatial structure. It should have some causal structure, but that should depend on what it's sampling, right? So basically the idea, the way you kind of start to think about that is think about defining a kind of a three automata that are coupled to one another. And you might think about one of them as being some kind of later on to become potentially global parameters that look like time. And they're coupled to something that later on will look like node states that look like states of matter. By the way, running some kind of dynamics on their own. Coupled to some kind of edge automata that look like causal structure.
I see.
And then the idea of indistinguishability is that really the fabrics, unlike automata of all this, you study equivalence classes of these things that are fuzzily connected to one another and to their environment.
I see.
So the idea is in the way is that you're never quite seeing the full picture, if you like. And then the question is that, so I'm just assuming in the starting case that, hey, because this is now my modelization conception of reality, I'm looking into it, but I'm just seeing Demis. And I look an hour later and I still see Demis, but now he's in a different pose. And we do this repeatedly, and it always works. So why? So the idea here is that here's why it works. Because it turns out that those fuzzy, indistinguishable collections of experiences, sometimes as they evolve in sort of different branches, the question is in a way is that, so here if we're sort of down to candidate time 10 in the future, I have 50 branches, and now I'm still just seeing one Demis, but now he's smiling, right? So somehow what has to be happening is that actually the probability distributions of all those different structures have to be equal. So you get these huge collections of polynomial constraints, right? And sometimes they're solvable and sometimes they're not. Sometimes the solutions are complex valued and sometimes they're not, right? And now what you're slowly starting to build is, now we're slowly building a model of Demis, the thing made of matter that has well-defined attributes, and time, right? And then, once you've done that, then I need to permutate all the pieces of him around until I noticed that, hey, when I kept the ordering like this, I always get Demis. When I permuted it thusly, I don't. So now suddenly my indexing set is getting ordered. And sometimes that has a set of solutions and sometimes it doesn't. Right? So, I mean, this is really kind of, in a way, this is easy to do. And the sort of, I think the cool duality here is that if you think about it like this, that now I'm kind of trying to lean on a bunch of math, like polynomial structures, to try to make a kind of a field theory of Demis, you know? And I actually, literally, I can piece it out from all these different possibilities. So it's not like the multiverse, it's the messiverse. From all these different possibilities, I'm picking the one that sticks together, right? And it turns out that in order to do that, I'm leaning on these polynomial structures. But the interesting way to think about this is that it's the other way around, is that I already believe that my experience of Demis is for real. So then, if you take this whole contraption the other way around, what are you getting? Well, actually, I would argue too that you're getting definitions of lots of mathematical structures that actually originate from your perception of, you know, observed physical reality, right?
So you conditional.
Yeah, either way, right? So I can say, hey, I want to believe in these mathematical structures with those constraints accessible to me. Can I make a Demis from my sort of big pack of fabrics? Can I knit the tablecloth? And each one of the tablecloths is kind of like a theory. So it's a modelization of my experience. As there are more experiences, the modelizations evolve, right? And again, experiences of models are also experiences. So and I think this is part of the things that in the beginning can be very confusing. So this kind of structure this kind of modelization can eat other models, right? So it doesn't just have to eat what it sees when it looks out the window. It can sort of eat a conversation with, you know, Hugh and another one with Demis, and it can think about Goodstein, and then actually a different kind of a modelization emerges, right? So, yeah, sorry. Yeah,
yeah, I just wanted, this is actually has some relationships to a discussion we were having last night, which is what happens in the special case if you take these fabrics, you weave this model, you've come up with some way of making sense of your experience, but the story you weave, or the model you weave, itself says, and this isn't because this isn't constructions of experience, it's the way things really are objectively in the world, independently of me, before, you know. So right now you're pointing out that it's, you know, it's experience of experience that's primary, and from that we construct our models. And fine, but what happens in this special case where the story that's constructed says, and this is true independent of experience? Do you think that's just false and it's a story that might be useful but it must be incorrect because of the rest of your position? Or do you think that actually maybe there's a different kind of eating of itself? You actually kick away the ladder and now you do have a realist view that started out looking like an idealist or subjectivist view?
Well, I mean, I think that there's one confusion here, which is that the way you're talking about it is that where I would start from is first I would try to construct something from experience that looks like a set of well-defined symbols, on top of which I would look at which kind of dynamics are actually preserved on top of them, or in this case I would call them computations. Then I would look at the kind of sentences that can be constructed. Now I'm going to think about those symbols as a language, or some kind of a model of arithmetic. And then I would say, well, what sorts of things can be said by this thing? And I would say, well, that's all very wonderful and exciting. It doesn't really change anything about the modelization that I just described to you of experience. So even, you know, no matter what comes down the pipe.
Even if it makes claims about that process, or even if it makes claims about reality that are conflict with what you're just saying about reality, which is there's this long fabric.
Yeah, and then I would just say that, hey, wonderful, I'm seeing another aspect of the manifold of all experiences. So the point here is that, seriously, I think if you think about it, is your experience is always limited. That's certainly that's what I'm hypothesizing here. So there is no contradiction.
It has to be because we're inside looking out.
Well, I mean, I don't know, but I mean, let me put it this way, Basil. That I did that and I tried to do it super carefully. And the cool thing is, I did make a thing that can make all the stuff that you guys spend a century building. That's amazingly complicated, right? And the point is, not all of it fits together. That's actually the whole new idea here, in a sense. right? It's not meant to fit together necessarily through some formal system. It's not that there's some reductive hierarchy. It's more like there's a forest of related things, and the link between them, the kind of the connective tissue, is this idea of modelizing the experience of experiencing. So, you know, when you make statements to me about sort of this idea that, hey, one of these models makes some statements about the truth of something else, to me that's just another experience.
But is there anything that would falsify? I'm not saying there should be, but I'm just asking, is there anything that would falsify the
model?
Yeah.
Absolutely. Any experience you give me, any theorem you give me, if I can't reproduce it, I'm out of the game, right? And by the way, it's very, very likely that fabrics as a kind of the current modelizing language of choice will turn out to be a frame, for example, that may not be suitable for addressing the kinds of things that Hugh's worried about. And then what I would say is, hey, okay, I need a new frame, but the sort of the conceptual framework would remain the same. So absolutely, this is very. If I can't reproduce this, you know, soda can, that's it. I'm out of the game.
But what about if you like, the metaphysical assumption about experience being primary? I'm not saying that metaphysical assumption should be falsifiable, but I'm just wondering, is there anything that would make you doubt that, or?
Yeah, absolutely. That's what I just said, Paavo. Basically,
okay,
like, if I can't produce something, I would go like, well, man. I mean, my first kind of like, whatever, like my first sort of victim would be like, oh no, my fabrics are not fancy enough, but my beautiful conception survives. But then, of course, you know, I would start to think, hey, no, there's something's fishy in here. But it is pretty cool in a way that you can make this kind of a modelization, and you need to make a couple of funny assumptions. There's no thinghoods at the bottom. There's just experiences. That's a new kind of a category of. Maybe even, I always worry about using these kinds of words with mathematicians in the room. I don't mean anything technical by it. I mean, there's new kinds of stuff in town, and you know, thinghoods are made from our experiences and other experiences.
Can I just make a comment? I
Yeah.
think it's very much like Grassman. I don't know whether you've actually looked at it. It's exactly like Grassman. So that everything starts from process, not from things.
Yeah.
And,
So
the things are then the invariants in that process.
Yeah, well, that's how you're going to kind of to answer Bert's point in a way. But that's why, in a way, I hone in on Demis, because that's how I'm sort of stabilizing the sampling.
Well, what triggered me is that you talked much about sampling, and you know, there's a problem. There's a basic problem to get quantum effects by classical sampling. So
Yeah, but this is so there's details here to the indistinguishability that actually go beyond the way you think about traditionally the classical, non-classical boundary. So because basically what you're thinking about is kind of the type of statistics that you usually think about as being generated by a Hilbert space model.
Right.
Well, but we know by these Tonia, Sin and others that actually there's a device-independent way just to look at those statistics. I'm just saying to you that the indistinguishability model is capable of producing those kinds of statistics. And also classical statistics.
But I would just like to say that line that we've made permanent is not permanent. There is one universe. We have processes which are classical, processes which are quantum, and we have to understand what the relation between those two processes are.
And I'm actually saying in a way that none of that really is the thing. It's that those things have utility, right? That it's not, experience is what it is. Yeah. Just because in the way I noticed that...
Please, all I was saying that these are models.
No, that's right. Yeah. And I totally agree.
It's the experience, it's the process behind that.
But you can definitely produce quantum effects in these types of models. In fact, I mean, I showed that in my D-field thesis that you can. I think most people, I didn't make a big deal out of it, but you definitely can do it.
But
the math is actually pretty simple.
You know about the sign problem, that you know that you have these negative problems. That are
Absolutely.
So this
Absolutely. This is a very natural.
This is a nightmare, computationally.
Yeah.
And so I would imagine that in your system it would also be a nightmare.
It's very hard to compute, and you know, this is when you start to. I used to always say to Demis that the stuff that we're trying to do, it's not expensive. It's just bloody difficult. And then I said, but the day will come when it's no longer difficult. It's just bloody expensive.
Oh.
So we need access to big sort of compute power now to because in a way, I mean, I will just say this about the human mind and / brain. Wow, it's amazing how much stuff we can do, especially collectively over a few millennia. I mean, it's...
Sorry, can I just say, what was the specific objection that you had?
So, you know, so the way that you can model classical distributions by sampling and you get statistics.
Yes, but you're in a different game. Change the game. Change the game. That's what I've been trying to do. That's what emphasising the algebraic aspect. Metaphysically, an algebra is about process. It's not about things moving in space and time. It's a process from which we construct space and time, aren't we?
I was triggered by the word sampling, so which
I was thinking, sampling's a different word. I wouldn't use
sampling is probably a bad choice of words, similarly to using the word category here. So what I really mean is there's a very specific set of models of what I mean.
It's not the Monte Carlo sampling.
No. It's a model of indistinguishability. And when I say sampling, what I mean is that I made a mathematical model of the idea of thinking about the experience, limited experience of experiencing, the manifold of all experiences. And I said, kind of like sampling. I should have probably not used the word sampling because it makes you think of something different.
It's difficult to know what words to use. We really need new concepts here.
But the good news here, Bert, is that the math checks out. So we can take that part offline, and in a way, I don't mean sampling at all the way you're thinking. I mean that I've made a model of the limited sense of experiencing something that can always be experienced more. And the interesting consequence of it is, I think I can make all the models that you've ever seen, and then it's on. With all of their mathematical properties, all of their spatiotemporal structure, all of their action principles, still outside of those models, by the way, but I now understand why they're actionable in the physics context. And they exhibit, by the way, both classical quantum and what I would best call for now post-quantum kind of actual statistics. That's the idea. It's a little bit out there, but anyways.
But then when you select a set of experiences, you are kind of projecting into a subspace of experiences, and you are losing...
You're losing a lot.
Okay.
And that's sort of the whole idea that actually my version of what happened here today is it's the story of that loss. It all seems super weird because in a way, the other way to do it is that, hey, I've now come up with the most awesome model of all. This model captures all others. And actually all experiences when I look out the window surely must look similar to me to this model. And here, what I've done in a way is I flipped things around and I've said, actually that can never be done. So I've just given up. And I've said, but anyways, where did all those modelizations come from, right? And how? And how are they related to one another? And then you can sort of say to yourself, in a way it's amazing, and separately amazing, for example, if you think about what for example, Hugh was talking about, that how much of our experience of the mathematical universe can be maybe covered in just FBA. Right? That's sort of a separate, that's to me like an intramodelization thing that's completely amazing, but in and of itself not surprising. Right? Does that make sense? Giulio?
Can I just engage in what you asked us to do, which is translate between languages around the table. And I think it has to do with various uses of the notion of model. So my verbal observation is very simple at the level of dictionary. It's kind of separating the notion of model, which is like a photograph. Here's a model of Joseph Almog, his passport photo. So there cannot be such a model unless there was Joseph Almog. It's induced by Joseph. And then there's another notion of model of Joseph Almog, which is, someone who never met Joseph Almog is doing a lot of points on the blackboard, and it turns out to be isomorphic to how I look.
Yeah.
And it's not separable from the passport photo, right? Okay, that's a kind of cosmic accident. Okay.
Yeah.
And I think in the air are these two notions of model, one which arises from the reality, or what you call the manifold world, and the other which kind of applies, it's Wigner's problem, the unreasonable effectiveness of mathematics in applying to physics. And I want to say that one of the things that are very nice about what I understand you to be doing is that I think a lot of people understand Woodin as if he was Gödel. Gödel thought that, so to speak, models, the richness of the spectrum of models, which are really sets at the end, so to speak, is the mathematical universe, what you call, is much richer than physical reality. You know, the Wirklichkeit, the actualities for Gödel are just a low, you know, kind of application. And
if I may say,
that's the Platonism. And I think what you try to do, if I understand you, and that's the way I understand Woodin, though Woodin would probably not say that because he's a very cautious man, is that this cannot be right. That, so to speak, the universe of sets must arise from physical reality.
Yeah.
There isn't another place where we're kind of assembling the universe of sets and then, whoa, it applies to physical reality. Physical reality, I mean your manifold of all experiences, is the source of...
well, that's certainly the conception here. It's important. Maybe I'll leave you with this thought and we move to other conversation. But, so on one hand, maybe it sounds like Ron was sort of saying, but what if your things tell you funny stuff? I would say, great, I have more experiences. But just to be very clear, that has nothing to do with this not being falsifiable. This is extremely falsifiable. So if someone has a model or an observation that this kind of approach can't reproduce, something's wrong with the approach, right? Either it's the modelization frame would be my first stop, or then the conception itself is broken. But anyways, I want to thank you for listening to me, and thanks for being here. Thank you. And miraculously, it's pretty much 5 o'clock, I think. Is that true? 2 minutes. I feel like,